Hello. I was said to wait 3-4 minutes more. Be patient. Thank you. It seems that the two first speakers are coming late. Then have to wait. Okay, sorry for this small delay, and thank you for waiting. Well, good morning, everyone, and it's a honor, and I want to thank Pascual for letting me the opportunity to give you the welcome to this 7th edition of the Photonic Integration Week. What was born as a meeting point for an emerging community 7 years ago has become the link of the integrating photonics value chain in Spain. During these 7 years, an effort has been made to make the Photonic Integration Week a bridge not only between the different research groups of Spanish universities, but also between academia and industry. Proof of this is that, along with academic talks, in each edition, the focus has been on B2B meeting sessions oriented to generate collaborations and projects. In this way, more than 350 B2B meetings have taken place, generating a strong cohesion between the ecosystem. During these years, we have seen many Spanish universities developing papers and patents about photonic integration, but also a growing group of spin-offs such as VLC Photonics, Ipronics, Catepov, QSight, or Material LiDAR, Fila, BMagine, BioHerent, CalSense, Medlumix, and many more. Now, in 2024, we can say that we have an ecosystem ready to grow and generate impact and value. Integrated photonics is ready to connect with microelectronics and lead a new era in which the development of chips in Spain is possible and becomes an opportunity for the future generations. Sorry, I'm feeling bad. Sorry, I'm feeling bad. No sé, tengo un pinchazo aquí. Sí, sí. Sorry, I had something here at the beginning of my chat. Sí. Okay. Sí, continúo. Okay, I continue. Sorry. I see new people here who were not a few years ago. Just to tell you that this is not a trend. We have not gathered here just to take advantage of an opportunity. 7 years ago, the Photonic Integration Week was born, and at that time, we created a large panel, I remember, on this wall, in which we visualized for the first time the value chain that we had in Spain. 4 years later, I remember Pascual and Jose Capmany created a document where they put for the first time, for the second time, the Spanish value chain in a document, and 17 other entities collaborated at that moment. Then it's not something that we created 2 years ago or something new. I think we must celebrate our country's commitment to this development with the creation of the partnership and the investment of a huge quantity of capital. It's a great opportunity that we must not fail to take advantage of as a sector and as a country. As we say in Spain, it's a trend that we shouldn't lose. And furthermore, here we have for the first time a leading venture capital firm in Spain, Bullnet, as a platinum sponsor. We no longer only have scientific knowledge and entrepreneurial talent, but we are accompanied by the public support and also the private capital. The future only depends on us. There is a lot to do, and although we have a lot of talent, we lack arms. Our critical mass is still low, comparing it with other areas of the world specialized in the development of photonic integration. Therefore, it's time to leave egos at the door and collaborate to grow together, joining efforts to turn our dreams in reality and start developing a big group of companies in Spain developing chips. Thank you. I'm sorry, because I had something in my lung at the beginning, and I didn't want to stop, but it disappeared. Sorry.
Thank you, Sergio. We hope it was just the motion. Okay, so welcome everybody. I can't do it by far any better than Sergio did in the presentation. So what I will do, I will just give floor to the first speaker, which is Guillermo Gomez from SEMIS.
Hello. Thank you, everybody. Thank you, the organization, for inviting me here to be part of a group of such a full-on experts group on photonics. My name is Guillermo Gomez. I am the technical director of SEMIS, which is the public entity for the microelectronic and semiconductor sector, which is in charge as the technical office of the Special Commissioner for Semiconductors to develop our dedicated plan for semiconductors in Spain with 12 billion euros to be spent or invest over the next years. Okay? So the objective of this strategic plan, the so-called PERTE chip that stands for the strategic project for the recovery and transformation of the economy in Spain. The key objective is to develop the scientific design and manufacturing capacity in the microelectronic and semiconductor sector in Spain. It is a part of a more ambitious transformation plan of the overall economy in Spain, in focusing on the digital and green sectors. But in this case, as a part of a 30 billion plan for digital, we have a separated 12 billion plan for chips only. That national initiative is to be seen as a part of a broader initiative, especially aligned with the European Union, along with the CHIPS Act, the European CHIPS Act, and especially the CHIPS EU as well, to reinforce the R&D capacities in Europe. Well, the PERTE chip is defined along 5 strategic assets to reinforce based on our strengths, to reinforce our scientific capacity. Even though we don't currently have manufacturing fast capacities, at least at great scale, we do have some strategic assets to develop this strategy. One is the RISC-V. So we are one of the countries mobilizing more resources to RISC-V. We have a flourishing fabless ecosystem on RISC-V. Second is the integrated photonics, and I will explain it later. Third is the quantum computing and the quantum technologies in general, both at the supercomputing capacities and at the service level as well. Fourth is micro fab. This is the name of our national research network on semiconductors, the public capacities. And 5 is the driving sectors, which is the sectors that consumes this kind of semiconductors and microelectronics, such as the automotive sector, aerospace and defense, and so on, including telecommunications. So here we have the photonics sector. I think I've taken this slide from Sergio. So Spain is one of the leading member states in the European Union that has an end-to-end value chain in photonics. That means we have the R&D capacities, which leading institutions such as Polytechnic Valencia, University of Valencia, ICFO, Centro Nacional de Microelectrónica, and many others. We have foundries, both at the national public institution and the regional ones. We have a flourishing fabless ecosystem with some of the key companies based in Valencia. We have equipment manufacturing. We have the end user consuming this equipment, and we have the association to connect all the agents. Based on our 5 strengths of the birthday chip, we have 4 component plants to increase and enhance scientific capacity, design, fabrication plants, and the ICT industry, which are the components consuming these semiconductors. So I will explain in a nutshell what the birthday chip is about. So the 12 billion plan is divided in 4 components. The first is the scientific capacity, which is, well, normally we will reinforce what we have, and we will finance new infrastructure in different areas. For instance, in microprocessors and new different architectures, such as RISC-V or others. Second, photonic integration, quantum computing, or other ongoing initiatives such as the IPCI on microelectronics as part of the European plan. The second component is the manufacturing capacity. By this plan, we want to, well, it's twofold. We want to attract foreign investments, big investments to Spain, either in front-end or back-end, or equipment manufacturing, or substrates manufacturing, or other part of the value chain. And second, we want the national capacities to increase. Maybe not at larger scale, but at some, well, relatively big scale, if possible. The third axis is that is not the third, it's the second, but the design axis is, the idea is we want to help the fabless ecosystem to scale up. So we do have a diverse fabless ecosystem, especially in Valencia, Catalonia, Madrid, and in many other regions. But these companies are relatively small, not all of them, but relatively small, and we want to provide financing and other instruments from the public sector to help these companies to scale up and compete not only at national and European level, but also internationally. And the fourth axis is the ICT manufacturing through the CHIPS Fund. Okay, I will explain the instruments. So basically, the instruments can be divided in four areas. The first will be the strategic investment. The strategic investment will be aligned with the CHIPS Act, the European CHIPS Act, and will mean every kind of public support to manufacturing facilities under the so-called figure of the so-called first of a kind requirement of the CHIPS Act. That means new manufacturing facilities that are not present right now at EU level. Okay, both at technology level, process level, security reasons, and many other reasons. So the idea is we can allocate grants to those facilities that are willing to be installed in, or are willing to come to Spain. And basically the way of funding these facilities will be through the so-called funding gap. So the funding gap is the difference of cost between installing this manufacturing facility in Europe, in this case in Spain, versus installing this manufacturing facility outside Europe, like the East Asia or other regions. So basically, the aim of the European Union is to cover the difference of cost. On top of that, we can provide equity. So potential equity participation by the public authorities, the states, in this venture, or together with industrial partners. Okay, this is for the strategic investment in front end, back end, substrates, equipment. So everything that falls under the scope of the CHIPS Act. The second way of financing is, well, the mechanism that the public sector is used to implement, which is the open calls for R&D. So we can go through grants, through competitive calls, for instance, for design centers, clean rooms, for industry, and many others. And we can do also direct investment in public infrastructure without competition, or with competition, and cooperation agreement with third parties. For instance, with a recognized R&D center, even nationally or internationally. Then we have advanced manufacturing incentives to support everything that doesn't fall under the first measure. That means relatively small manufacturing facilities. Okay, we are talking about big manufacturing facilities in the cases that the investment is more than 150 million euros, or 1 billion euros, 2 billion euros. So the foundries that are being installed or about to be built in Germany with Intel, in Ireland, in Italy with ST Microelectronics, or Global Foundries with ST in France, for instance. So basically, we can allocate grants through competitive calls to small projects for fabrication. And we can also complement that with loans or equity through the CHIPS financing facility. And the last, we have the CHIP financing facility, like a measure to complement all the grant part, offering financing through equity participation, loans, even at commercial rates or subsidized if viable, or a combination of these measures. Okay. The aim of the CHIP financing facility is to help any type of business to scale up, including startups, scale-ups, or consolidated projects that need to increase the capacity. Even for design, manufacturing, substrates, the whole value chain of semiconductors, including ICT-related industry. So the big consumers of chips that will drive and pull over the supply of chips. So these are the instruments, and this is what we have right now. This is the implementation phase of the chips, of the per chip. If we look to the right, the up-to-date investment we mobilize so far from the per chip office, we launched different R&D programs. First of all, we launched the chip missions, of which we have allocated 50 million euros to reinforce the microelectronics and photonics ecosystem, both for microelectronics and with a dedicated thematic on photonics as well. So the idea of these chip missions was to form a public-private consortium with the obligation of subcontract some R&D institutions as well, public institutions, to work in different technology areas that will develop prototypes, new designs, and so on. Second, we have chip university chairs. This is very recent. It is not finalized yet, but the temporary resolution has awarded 45 million euros to company university chairs. The aim of this program is to create public-private chairs at the university in various domains, such as photonics, to increase the generation of talent, okay, very rapidly, very quick. And then we have the IPC of microelectronics. The IPC on microelectronics at the European Union will mobilize 8 billion euros, of which 500 million euros is a Spanish contribution. And basically, we got the green light from the European Commission to spend these 500 million euros, or to finance up to 500 million euros in grants, but that will finance basically RISC-V, packaging, photonics, and communication. We already granted some of these 500 million euros in RISC-V and photonics and packaging, and there are some of the money that will come in the following months. And the last, we have the proof of concept, which is this is a competitive call for the public sector only, universities and R&Ds, that is being managed by the Ministry of Science to foster, well, to help the research centers to develop new prototypes, new proof of concepts, new experiments, and new, well, research activities in the field on semiconductors, including photonics, okay? So all of these programs have a lot of photonic contents, and so congratulations to the sector, especially the Spanish sector, to for your participation in this course. Regarding the strategic investments, well, the latest announcement are the Intel Barcelona Supercomputing Center engagement to build or to cooperate in the new post-exascale lab for quantum HPC, high performance computing, in RISC-V. Second, the Cisco Design Center that will open the first in the EU design center of Cisco. Okay, that will be the main design center in Europe. Third, we have the Broadcom. We signed a letter of intent with Broadcom to develop a new flip chip VGA substrate, backend substrate facility, and we are working in the details with the European Commission through the CHIPS Act at the moment. Okay. And fourth, we have IMEC. IMEC, we also signed a letter of intent with IMEC to establish in Málaga a new facility, a new R&D fab for semiconductors as a complement to the main installations in Leuven. Okay, we are working in the details, and we will provide new advance shortly. Okay, so this is the status of the partnership. We have lots of ongoing operations, especially through the CHIPS financing facility. And if we look to the left down, what are the next step of opportunities? So right now we are thinking, well, this is still pending, okay, because we need to see what is the visibility in terms of budget and planning. But normally we will be able to set up the partnership financing facility very shortly. And we can think in clean rooms programs, both for public and private, pilot lines we are willing to support pilot lines, especially in photonics, through the CHIPS EU initiatives, design centers, competence centers through the CHIPS EU as well, or advanced manufacturing incentives. So this is these are examples of the programs that may eventually come over the next months. Okay. So where we see the opportunities, integrated photonics, of course, new equipment manufacturing, new materials, critical supplies, power electronics, mid-range and mature nodes for vehicle telecom industry. Okay, even if we talk about mid-range nodes, there are a lot of innovation to happen in this field as well. that qualifies under the first of a kind from the CHIPS Act. Advanced packaging, of course, combined with photonics, graphene, quantum, or new R&D lines. So, last, I want to thank you for inviting me to this conference. And as a conclusion, Spain has dedicated a massive set of resources to develop the semiconductor industry. Okay, we mobilize 0.9% of the total GDP of Spain, 0.9%, which is a lot, more than other countries that are mobilizing 0.2, 0.5 of their national budget. So right now, Spain is the place for investment. We are very well positioned because maybe I miss it, but on top of that, we have strong GDP growth and low inflation. So okay, we are one of the economies that is performing the best in Europe. Highly qualified talent pool, this is the proof, we have it. Hosting such as important events in photonics. Abundant renewable energy, this is very important, not only for the foundry, front-end manufacturing facilities, but also for the ICT consumers, such as data centers, for instance, hyperscalers and so on. We have extraordinary logistics capacity as well. Excellent wave adjust productivity, a strong customer base in telecom. We are the second vehicle manufacturer in Europe, the 8th in the world. And the business-friendly policies such as this very program. And a privileged geopolitical location, which is very important in this geopolitical biased sector. And top quality of life. Well, hosting this kind of events in Valencia is a proof of that. So we are from the PERTE and SEMIS, this public entity, we are waiting for your proposals. So if you want to invest, you have an idea of project in photonics or in other sectors, please come to us, explain your idea, and we will be happy to listen to you and to find the most suitable way to support, because we think in the Special Commissioner for Semiconductors we need to cooperate together as a true public-private cooperation, and that will be the success to it. Okay, thank you very much again for the time, and thank you.
Thanks, Guillermo, for the talk. So now we have some time for a few questions, Guillermo. Guillermo, we have some time for questions. Yes, yes, a couple of questions. Anyone in the audience, please?
Sorry.
So you're forcing the chairman to make a question, right? So Guillermo, how do you see everything in terms of end dates and timing, right? Because the program is already running for 2 years. Do we have some hard deadlines on the program, or this is something that can be somehow extended?
Well, the money comes from the addendum to the recovery plan from Spain. So these funds come from Europe, okay? So we negotiated the way of implementing these plans, these funds, in a way which is flexible enough. So that means the formal deadline is the Q2 of 2026 for implementing, well, for this cited the implementing instruments. But the milestone is not to finish the project, but to disburse or mobilize the money from the public authority to the companies or the national institutions or the public institutions. So that means as long as we give the money to the final beneficiaries no later than the Q2 of 2026, we are okay, even if the project develops later on.
Okay, thanks, Guillermo. That's important information. So, any other question there? Yeah.
Good morning. On this topic of timing, what is slowing down the deployment of funding at this point? Is it a lack of project, lack of private commitment?
Well, as we can see in this, when the previous slide, we already mobilized more than 600 million euros. So I think we are on time we are on track. Okay. So it is not the lack of projects. Okay? We are listening to many proposals. Yeah, this is the slides. We can see we have foundry opportunities and the opportunities with Broadcom, IMEC, design opportunities. And regarding the chip financing facility, even though it's not formally set right now, we are also evaluating the proposals at the moment. We have more than 40 projects being evaluated at the moment by the office. So hopefully we will start in the coming months to announce the investments that will be supported by the partnership. Thank you.
Okay, so I think that we need to move on to the next speaker. So let's thank Guillermo again. Thank you.
You're welcome.
Okay, so next speaker is Joris van Kampenhout. I don't know if I pronounce it right. It's okay, thank you. From IMEC, so the floor is yours. Thanks, Joris.
Thank you, Pascal. And thanks again for the kind invitation to speak here today on behalf of IMEC. It's a great pleasure for me to reconnect with the Spanish ecosystem in integrated photonics, which is growing very nicely. So today I will talk about integrated photonics at IMEC. Of course, IMEC, we really focus on silicon, right? So that's why I added the word silicon to the title. But I'll try to give you a bit of an overview. For sure, I will miss out on a few things because there's so much going on in IMEC in photonics, but I will try to touch on the main themes in the next 15, 20 minutes. So for those that are not aware about IMEC, I just inserted this slide. We are arguably the biggest European independent R&D center. We are non-for-profit. And our main focus, of course, what we are very well known for is CMOS core technology scaling. That's still the core of many of our activities. But we're also expanding into different application domains. For instance, healthcare, energy markets have been becoming more and more important over the past several years. And across that full span of activities where we are serving today already more than 500 companies. So we've seen very nice growth over the past several years. Our budget is now exceeding 800 million euros. And we have more than 5,000 people. It's a very international place to work. So it's definitely a thriving environment to do a cutting-edge R&D. As you will see in the next slide, we also have a quite unique infrastructure that was built over the years. That's located in our main site in Leuven. And besides kind of serving big and smaller companies, we have also increasingly started to generate more spin-off companies. In fact, now also a dedicated venture fund, IMEC Expand, which is helping to create more spin-offs. So talking about the infrastructure, here's a bird's eye view on our main site in Leuven. So IMEC has multiple sites across the globe, but I would say the anchor point today still for sure remains in Leuven, where we have our main clean room facilities. So here you can see how they are laid out on our site. So first on the bottom, you see our 200 millimeter clean room. That's the older one. So that's where we have, I think, our more mature technologies established by now. So silicon photonics is one of them. Some of you may be familiar with our offerings that we have in silicon photonics, like the ICIP platforms, either in MPW or bilateral engagement. We also there have a GAN silicon platform running, and there is a quantum computing lab established there as well. So that's where we have, besides our more mature prototyping and low volume manufacturing platforms, so that's happening on 200-meter wafer size. Now, what you see on the top right is our more recent fab, which is also extended already. And so in that fab, we do our more advanced R&D work. Of course, that's driven to a large extent by the advanced patterning. So we have very advanced patterning capabilities, high-NA, EUV. And we are also doing the advanced research into next generation transistors, memory systems. It's not mentioned specifically here, but in fact, we also have a fully functional 300-meter silicon photonics platform running there. It's not offered yet to external customers. But it is the place where we do our internal R&D, of course, also combining it with advanced 3D packaging technologies, such as hybrid bonding. So that's definitely something that we are preparing for. And at the right time, we'll also start offering that capability to a wider audience. And besides that, of course, we have many new emerging application domains in the sphere of bio, also with the all dedicated lab, hyperspectral imaging, smart sensors. I will not touch on those today, given the time limitation, but you can see it's quite comprehensive kind of coverage. So moving back to the field of integrated photonics, I wanted to make the point that, of course, photonics is a very wide technology with many possible use cases and also different implementation methods. I mean, you can choose a variety of plethora of material systems. You name it, in fact, it may have an optical use case. But from a market point of view, in the next 5 years, we believe the market will still be dominated by optical interconnects, right? So here you can see an example market forecast by Yole that predicts that we will see very healthy growth, specifically in the field of datacom pluggable optics, but also more integrated versions of optical transceivers are coming to the market with very strong growth rates. And you can see that the overall growth rate for silicon photonics, so the wafer die revenue, is more than has a growth rate of more than 40%. So it's very, I would say, impactful on the overall industry. And of course, we've seen recent announcements from major foundries like TSMC, but also Intel and global foundries that the big guys are really starting to get involved in a meaningful way. And that's really driving the ecosystem, industrial ecosystem towards bigger engagements. Of course, the big elephant in the room was driving all that growth is AI machine learning, where it's, of course, something that we are all exposed to. We have seen a massive uptake in advanced compute capability happening in the cloud data centers, specifically in this kind of AI machine learning clusters that contain tens, hundreds, even thousands of these compute nodes using the most advanced logic. And so we see they're doubling every 6 months of the compute capability. And that's really driving the growth of the industry, I would say the semiconductor industry at large, but also, as you will see, the photonics industry specifically towards optical interconnects. Because one point that is becoming more obvious is that while logic scaling has happened according to Moore's law, the scaling interconnect bandwidth has been much slower the last 10, 20 years. And you can see here the gap is opening up wider and wider. And that's really kind of choking the system level performance of the most advanced AI machine learning clusters. So that interconnect bandwidth happens at different interconnect distances. Of course, for optics, we are looking more at this kind of several meters and tens of meters, if not hundreds of meters interconnect. And that's, of course, why you see the most advanced leading companies in this space also starting to deploy massive amounts of optics in their systems. So here you can see, for instance, an example from NVIDIA. That's their H100 system. Meanwhile, they come out with a new version, but that previous version, you can see here as 2 optical networks, one kind of an Ethernet type interconnect using either single mode or multi-mode optics, pluggable optics. But then also in yellow, an additional network that's really for GPU to GPU interconnectivity. So you can see that the amount of optics being used in these systems is growing very rapidly. If you do the quick math, we are already at a run rate of several terabits per second of optical connectivity per GPU. And the next systems will have close to 10 terabits per second. So it's really escalating amount of bandwidth deployed per compute, to close that gap that I showed in the previous slide. Here's another example from Google. They also came out with quite some public information of how they have been putting together their AI machine learning clusters. They are arguably leading the innovation in the field because they're the first one to use optical circuit switching to interconnect all these different servers in their data centers. And I'm not the biggest system expert, but what they have been saying is that this really enables them to offer the lowest costs of ownership in offering these AI machine learning services to their customers. It's really driven by optical innovation at the full stack level, right? And you can see how that optical circuit switch design has then led them to come up with their own innovative transceiver architectures, where in fact they use a bidirectional kind of system where both the outgoing and incoming data stream is running over a single fiber, right? So that's you can see it's a full stack optimization starting at system level, but then going all the way down to the optical component level. And so bringing it back to what IMEC has been doing the last 10 years or so, of course, we saw what was coming in terms of the need for scalable optical interconnects. So we started back in 2010 a research program that was really focused on developing the scalable silicon-based technology to have that scalable optical transceiver technology implemented. And so we've come a long way along the years, starting off with the basic research. I mean, in fact, it dates back to 20 years at the early days in Ghent University, where there was a few master's thesis topics that were dealing with the first waveguides using a silicon infrastructure. But over the last 20 years, we're able to add all the functionality. So high-speed modulators, and we have the traditional Mach-Zehnder modulators. We have still more exotic modulators like ring modulators, electro-absorption modulators. We have been optimizing them for speed because in latest transceiver products, 100 gigabit per second is needed. Going forward, that will become 200 gigabit per second per lane. So, and that's where Silicon Photonics also excels in giving you that raw bandwidth, at least up to 200 gigabit per second per lane, in a way that you can co-integrate all these components on a single platform, and you can really leverage the CMOS supply chain to bring these products to the market. So besides active components, also detectors are there. Of course, we have also silicon waveguides, tight bending radii, high integration density. And more recently, we also started adding more silicon nitride waveguides in the mix to complement what we can do with silicon. So that technology is in fact being used today in some of these products. So pluggable optics down up to 800 gig. We believe that technology can scale to 1.6 terabit per second by going to 200 gigabit per second per lane. So you have seen in the previous slide that our technology is capable of doing that. But then this slide also shows you, as you go to these pluggable optics, how much worse your interconnect KPI is compared to short-reach electrical interconnects, right? So you see here in this chart as a function of interconnect distance, the key KPI of performance indicator for interconnects is a product of bandwidth density and power efficiency, right? So is that a product you want to be as high as possible? That's the best performing link. And so, of course, for very short reach electrical links, you're orders of magnitude better than what you can do with a pluggable optics. And of course, in these scaled out AI machine learning clusters, what you really want to do is kind of get the performance of a short reach link, but with a reach of an optical pluggable, right? And so that's really driving a major R&D team across the globe, I would say, and of course IMEC is also playing a role there to try to fill that white space, and I will come back in the next few slides how we're looking at that. Maybe just one more sidetrack here is for pluggable optics. They're also very cost-sensitive products, so driving down costs, reducing the dollars per gigabit per second is a continuous struggle, I would say. So one element we're also looking at in our platform is to add the light sources at wafer scale, because that can be another step to further reduce the cost of these systems. And so in the more near medium term, we believe that flip chip integration is probably a good avenue here, because you can leverage existing supply chains in 3.5. The downside, of course, is that you need to do pretty precise bonding of these 3.5 components with respect to the Silicon Photonics wafer, because you need to hit sub-micron precision. And that's where, of course, advanced packaging technology comes into play. So in IMEC, we've been kind of pre-developing that. We have developing these interfaces to host these lasers. Some level of co-design is required with the compound semiconductor vendor there as well. It's not a qualified process just yet, but we have some initial results that show we can couple quite a few milliwatts of light in our waveguides, and we are aiming to get more than 100 milliwatt coupled to our waveguides in the next couple of months. So pluggable optics, of course, will evolve. They will go to 3.2 terabit per second. Industry really wants to keep using that known implementation of optics as long as possible, because the supply chains are set up for that. So 3.2 terabit per second is very likely going to happen, but that means that we will need to scale our lane rates up to 400 gigabit per second per lane, right? So now, okay, that's quite some bandwidth we need to deliver, and that's where Silicon Photonics is starting to run out of speeds, especially on the modulator side. You can make very fast components, but if you do that at that speed, you will have a very lossy modulator, and then you will not be competitive from an optical power consumption point of view, for instance. So 400 gig per second is driving some additional heterogeneous integration requirements. Now, we will always need kind of advanced DSP and error correction on these optics at these speeds to close the link. So they will come down in power, they will go up in bandwidth density, but in our opinion, it's not the long-term solution towards lowest power efficiency. I will show an alternative how that we believe that can be done perhaps better in a longer-term approach. But for this 400 gig per second per lane kind of capability, more heterogeneous integration is needed. I think that some of you are definitely familiar with the theme of microtransfer printing. So it's, of course, kind of a generic technology that can be used to take this thin film, semi-fabricated devices, fabricating on a native 3.5 substrate, and then transfer them in a semi-collective way to the underlying target silicon photonics wave. So you can do that for 3.5s, but you could also do that, for instance, for materials like lithium niobate. Lithium niobate, you know, today is a workhorse in high-speed modulators, and implementing thin film lithium niobate devices on top of silicon photonics could be a way to extend the lifetime of this technology to 400 gigabit per second per lane technology. So with our associated lab in Ghent University, we have been doing already some pathfinding work on this field. So both on 3.5, they've done quite some very nice work over the past several years. More recently, also moving to lithium niobate transfer printing with some early demonstrations already showing that the concept works. Now it's really a matter of can we scale this to the right yields, reliability specifications. So that's still something that we need to work our way through. So beyond pluggable optics, we see that will scale a bit, but you see we need orders of magnitude scaling, right? I don't think that can happen with pluggable optics. So co-packaged optics is the next step, in our opinion, to get to these even higher bandwidth densities, lower power per bit. So to the level that you become competitive, let's say, with an electrical link of a few centimeters, but now you can run that link over tens of meters, or if not hundreds of meters, right? So with co-packaged optics, you bring your optical engine very close to the compute nodes at the same level, the first level package. That allows you to have much denser interconnect lines in the electrical domain. So that helps to be able to run at lower lane rates, so you don't go to the bleeding edge in terms of lane rates, but it helps you to work in a more power efficient parameter space, let's say, right? Of course, the flip side of that is that you have more lanes, and typically one of the key cost drivers of photonics has been that the yields, especially as you go to many, many lanes, drops off very quickly, right? So we need to find the right balance between lane rates and cost. But of course, in this more parallel integration approach, we can also leverage our advanced 3D packaging technologies that we can leverage from our colleagues in IMEC that are doing this, the CMOS hardcore CMOS scaling, right? So these advanced 3D packaging techniques can be readily used also for the optics integration problem. So here, indeed, wafer scale 3D packaging, but also in the optical domain, for instance, using more wavelengths, coming up with ways of doing more aggressive wavelength division multiplexing. Silicon nitride needs to be very low loss, needs to be power efficient. Packaging cost, I'm sure that Peter will talk about that as well in the next presentation, getting more fibers attached to your transceivers in a cost-effective way, in a reliable way. It's very challenging. And again, we will not work at the highest lane rates. We will keep them probably in the order of 32 gig per second or so, but then have many, many more of them. So we can run these links error-free without effect, which can help to reduce the power consumption. And so in IMEC also, that's part of our core research program, where we're working with the industry already for more than 10 years and doing that pre-competitive research work. Here you can see a recent demonstrator where our team put together a ring modulator-based transceiver. It was published last year at OFC, where we'll be able to kind of do an error-free loopback at 40 gig per second with a power consumption of just slightly more than 3 picojoules per bit. So that's kind of the proof of concept demonstration that we typically do. And then from this stage on, our industry partners will take it up and move it to a product if that makes sense for them. And then longer term, we even see a role for optics at this few centimeters range of interconnect. So bring optics really at interposer level, where now you're not going to go to fiber, but you're also going to start interconnecting the multiple XPUs, talking to each other with long interconnect waveguides on an interposer, right? In fact, some of our most advanced system companies are already asking for capability like that. So it's really escalating, I would say, the demand for optical connectivity. So that's, of course, still a bit further out from a product point of view, but there, and again, we need to be much more aggressive there as well on the power targets as well as the bandwidth densities. So that's part of, we're doing the early research work on the dynamic as well. At OFC, a bit later this month, we'll publish a few recent examples of these building blocks. Switching gears very quickly to a few other non-optical interconnect applications. So, of course, in IMEC, we're also looking ahead what's coming in the medium to longer term. And so one of these applications is in the LiDAR space, more specifically FMCW automotive LiDAR systems. So that's all about having long enough range, having a lot of, having good reliability on that LiDAR functionality also in adverse weather conditions. So it's a very tough problem to crack. And so it's still, I would say, a bit more in the research pathfinding phase, understanding what components are optimum for this use case. It shares a lot of similarities with some of the challenges we're seeing for transceivers, so that's a good thing, because this market will not drive massive volumes from the start, right? But it can likely leverage a lot of the supply chain elements that are being put in place for transceivers. So that's good. Of course, there's going to be some differences, and the question is, what are the key components that can link the aggressive system level performance to the underlying supply chain availability. So that's the research activity that's also ongoing, both on the light source integration, beamformer, but also on the detector side. If you have more questions about it, I can connect you to the people running this project in AMIC. Another emerging application domain is in the space of biophotonics, also photoacoustics. Again, it's not my expertise domain, but it's about using light at the interface between our human bodies and its environment, right? So, and there's a lot of kind of functionalities in terms of diagnosis, monitoring, intervention, therapeutics, where light can play a key role. Now, obviously, in this application space, you probably need more wavelengths than 1310 or 1550 that we're using transceivers. So, for instance, OCT is one of these areas where we have some research activity, typically happening at a bit shorter wavelengths compared to optical transceivers. There's also photoacoustics. Again, there it depends really what you want to measure. You can go also to longer wavelengths to measure some molecular bonds here. And then also, in the longer term, there's this vision that we can use light really to do the full mapping of metabolism in your body. Of course, it's a very long-term vision, very long-term dream. But a lot of sensors will need to be built in a variety of different wavelength ranges to support this vision. And so for that, of course, we can leverage part of the platform I showed you for optical transceivers, but more often you really want to do something dedicated here, right, for the core functions that you need. So here you can see our standalone low-loss silicon nitride platform, or at least one of the versions, where we have very low-loss silicon nitride waveguides, both for the current telecom wavelengths, but also longer wavelengths for some of these sensing applications towards the 2 micron wavelength range. But then also going to shorter wavelengths, we have some waveform maps of some more recently measured propagation losses. So at 640 nanometer, we're well below a dB per centimeter. At 450 nanometer, loss goes up a bit, but we're still quite competitive at a couple of dB per centimeter here. And so with that, maybe we'll go to wrapping up here, just to say that, IMEC has been in the game of integrated photonics for quite some time now, especially in the space of interconnects. We've come a long way from basic research, which started more than 20 years ago, then more than 10 years of prototyping, and eventually we're able to bring that to the level of maturity, that we can bring them to low volume manufacturing. So it takes time, takes investments, but it can grow very big if you have a continued effort in developing the technology. So we've done more than 100 tape-outs over the past 10 years, and we are working with some of the leading companies in the field here. And so going forward, I think just to wrap up, we really want to keep playing that role. Now, it's not just IMEC by itself. IMEC, its role and mission is really to work in an ecosystem, right? So connecting the great ideas in academic groups and further working with them to develop them, and then bridging the gap to industry. That's really one of our core strengths, building that ecosystem, right? And so that's, of course, part of the discussions and dialogues we also want to have with the ecosystem here. And with that, I thank you very much for your attention.
Thanks, Joris, for the presentation. We have some time for questions.
Joris, great presentation again. Very impressive technology. Just on the laser integration, how close can lasers be? Can they be on a single chip? Is there a minimum spacing?
That's a good question. That's of course always the question about, is the laser in or out, right? And I think in industry you still see both teams, right? I think there's a key concern about reliability, because once you put it in, you cannot replace it. Obviously, it will be much more difficult. So, and of course, you don't want to have a situation where you have all that expensive 2 nanometer CMOS node and your laser fails, you need to trash the whole thing, right? So that's a key concern. So now what is interesting is that, for instance, what Intel has also publicly announced is their integrated laser has better reliability than any incumbent laser because some of the failure modes have been taken out, right? So that's already one thing going for it. Now, and in addition, if you integrate it, you can also start putting spare lasers into your system, right? So these are kind of two elements that can help to mitigate a laser reliability issue.
Yeah. And can you put two next to each other? So can you do a flip chip and another one right close to it?
In the case of flip chip, we have some design rules here. I will not give you the exact design rule because I don't know at this point, but I think we have a minimum spacing, I think on the order of, depends on the system, right, that you use, but I think on the order of 0.5 millimeter today that we can, yeah.
Hi, thanks for the talk. I wonder how the thermal management is done in this packaging or in this heterogeneous, if it's local or if it's general, how you manage the thermal of, for example, of lithium niobate, indium phosphide, silicon?
Yeah, it's a great question because again, yeah, these systems, if you integrate, I mean, you're putting your let's say your laser in an environment that's going to be very hot, right? Because these systems are consuming kilowatts scale. That's massive, right? Now there's a lot of innovation happening on the thermal modeling, but also thermal management, including at IMEC. So I think the standards for these systems will be even water cooled, right? That's kind of almost a given that these systems are so heavy on power density that they will be water cooled. And there's only several of these system companies that are deploying that, including Google, right? They have this water cooled system in there. So that's kind of the boundary condition. Now that still means that you still need to do all the modeling from package level all the way to component level to make sure that your thermals are properly managed. It's a very important concern, especially in the context of putting lasers in these systems, because again, temperature will make them less reliable, right?
Okay. Any other question? No? Let's thank Joris again. So next speaker is Peter O'Brien from Tyndall.
Thanks, Pasquale. Thank you for the invitation. So I'm going to talk briefly about our pilot line, but I'm going to a little bit of a different twist on it because generally people think of pilot lines, they think about working with industry, and we do that, of course. But I think in relation to new programs like the CHIPS Act, there is a look towards lower TRLs. So I'll just explain what that means, but I think it's a very important kind of concept and something we've learned over the past couple of years in what we're doing in a previously funded pilot line. So at Tyndall, we started packaging about 2010 from scratch, and we've grown organically over the years. So I will say we haven't had major investments. We've had kind of, individual investments, but it's really kind of got, been quite a successful activity. So you can see here, for example, we're involved in the pilot line, which we lead PICSAP. We're involved in Europractice. These are just some flagship programs, but we have many, many individual projects. The Photon Hub Europe, and more recently in Quantum, the flagship. And actually Quantum, from a packaging perspective, is proving to be a real challenge, especially cryogenics. So material science is always a problem. A challenge in packaging, but even more now in quantum cryogenic. And the materials we use really just don't cut it anymore. We also have global partnerships, kind of like a smaller kind of analogy to what IMEC do, kind of an affiliation. And I think that's a really successful kind of approach where you bring companies on site. So, for example, we have Phycontech on site, we have Cellaprint, Joris mentioned, Transfer Print, 3.5 for example, on silicon. Cellaprint are a US company, they're located in our labs, and we have some machines as well from Cellaprint and engineers. And similarly with Phycontech, and I'll show you one or two examples with Phycontech which have proved very successful. And then, with these projects, especially with our pilot lines, we engage a lot with industry, very challenging timelines. Some of them are, really, really short, fast-term projects. And then some of them are more, long-term, and we build long-term relationships. Our biggest challenge, I will say, is we have many more projects than we can handle. We've got a lot of people coming in, so we're really happy to see other places, especially like in Spain,
developing up these capabilities, because there's a huge amount of work to be done. And also in the US, we're involved in quite a few DARPA projects, and Joris mentioned the increased capacity. So the biggest area we see, without a shadow of a doubt, in growth is around AI. So we're involved in a number of projects around that. I won't go into details, I can't really. But what I will say is, there is no doubt about it. Packaging, for example, in photonics, it's kind of been doing its own thing for many years. And it's really being brought in more and more with microelectronics, so microelectronic packaging. So that's really going to set the parameters and the boundary conditions of the kind of things we will be doing and using those resources. So we need to work more with electrical packaging engineers and kind of be more compatible with that type of industry. So just so people understand, originally when we were looking at the concept of a pilot line, it was really kind of like looking from research to volume manufacturing or medium manufacturing. And I will say over the years we've tried to do that. And what we've learned is that the focus is, from our perspective, is more to be the transition from research to manufacturing and kind of setting it up ready for manufacturing. And then working with our industry partners, and we still have gaps there, because Europe is doing pretty well as far as compared to the US, for example, in kind of that transition, but we still have a long way to go. So it's really that kind of TRL 5 to 6 is, I would say, is the sweet spot right now. And I'll explain a little bit about that in a second, where we see the future pilot lines. There's calls out at the moment around this area, but where we see that going. And we've given some input to the Commission about that. But just to look at packaging, and you may have seen this diagram before, and what I will say is it's quite complex, and really the way, historically we look at this, we kind of go from the micro scale and we look at fibers, we look at the interface, we look at the coupling, but more and more we need to look at the system and from the top down. So for example, the packages are getting quite complex. We're seeing huge numbers of increase in fibers, and actually I do believe in the future we will not be interfacing fibers with chips. We need to move to kind of optical interposers. And there's a big drive towards that, because there's a limited pitch that we can get with fibers. It's a chip-by-chip approach, so we can only package one at a time, whereas we've moved to wafer level, flip chip onto, for example, wafer level interposers. And I'll show you kind of some work we're doing in that area. But that definitely is, a very, very, very important area. The other thing about the system is, one of the big challenges we're seeing as we make these chips bigger, and we're looking at packaging on interposers, stress and warpage. Joris mentioned about thermals. The heat capacity, generation is huge. So in one of our more recent projects around kind of an AI type packaging on an interposer, the warpage was such that the large fiber array could not couple properly to the chip because it was bending. It was actually physically bending. We could not couple to the edge. So management of thermals is really, really significant. But just looking here, you see the different types of optical. And another problem is in packaging. I don't want to continuously kind of throw out all these problems. They're obviously big challenges. We see so many types of couplers. So we have edge couplers, we've got grating couplers, different types of edge couplers. There's undercut membrane couplers. There's edged facet couplers, there's mode size differences and so forth. So really there needs to be some more consolidation as well. So standardization and so forth is important. And then, looking at optics, fiber optics, micro optics, and there's different approaches to that. But as I said, the electrical packaging, I believe, is really where one of the biggest opportunities is. It's to become more compatible, integrating not just the chip on an interposer from an electrical perspective, but also optical interconnect as well. So a number of years ago, maybe 10 years ago, there were groups working on using the interposer, embedding optics in there. For example, IBM had developed that technology using evanescent coupling. It's actually having a resurrection, because as I say, the fiber channel density is really limited, and the pitch based on fibers. And then, as I say, you go across. Joris mentioned about active integration, whether that's flip chip or transfer printing, for example. Thermals are a huge issue as we go to much higher densities. So, for example, this is a project we're working Morphic and Formic. It's with Wim Bogaerts in Ghent. But you can see some kind of typical dimensions here. So the chips are enormous, and the fiber channels are increasing. You can see, for example, this ceramic interposer. So this is a high density, multi-level, microscale type interposer, working with Kyocera on that 20 level, 40 micron line width and spacing. And they were flipping the actual photonic device. I don't know if we have a laser pointer on this, but we're flipping the actual photonic chip, and I'll show one or two examples of this. And then the PCB is quite large. But the point I'm making here is these packages are getting bigger and bigger. Thermal is getting more challenging. So that top-down approach, not just looking at the micro level, micro scale, is really where you need to kind of consider all of this. So in a sense, we're looking at systems. Packaging really, truly looks at systems. So ultimately where we want to go is, and one of the things we developed in our pilot line was fairly simple design rules. So for example, we had Synopsys, formerly Phoenix, and originally we had this simple ADK assembly design kit, but just very simple design rules, and that's been installed in some of these software tools. And then that enables us to make some fairly simple type of open packages, and then more user specific packages. So these are standard types of packages, as I say, low cost, kind of off the shelf, where people can evaluate actually the chip, see if it's working, and then invest in a more expensive type of package solution. Be it, for example, a gold box, like a kind of an expensive butterfly style package. But again, some of these design rules, very simple, but they do make a big difference. So for example, here you see a layout of a flip chip, electronic IC on a silicon photonic chip. How you lay out your RF, your DC wire bonds and all that. And again, not being able to do that really inhibits you packaging devices. We've actually received chips which we couldn't package. And ultimately where you want to go with this, you have the PDK, process design kit for your foundry. Similarly, you've got a package ADK. And really the user then doesn't have to worry about how they configure things. And that's really where things need to go. So in a sense, you have this kind of co-foundry where you have your fab and your packaging kind of all working together. And that's really where things need to be. Over the years in our pilot line, we developed up with many foundries what we call reference chips. And this is a really useful concept. Essentially, they have a range of optical and electrical IOs. We can validate processes, we can validate machine installs, we can check different package configurations, and I'll show how we're using these, for example, on new glass interposer materials. And we've made those available, so we've got some standard chips, and for example, with Linex and other foundries, we've made quite a few of those chips, and we give them out to people, for example, if they're installing a new system, new machine. We know the coupling efficiency of that should be, so it's kind of like very good for an acceptance test. We've also worked with AIM Photonics in the US, and they've kind of copied these principles. So again, you can see on their chips, they have a range of optical and electrical IOs, and at the moment we're working on a transfer print. So they're opening up their silicon so we can actually transfer print, again working with Cellaprint at Tyndall, so we can kind of develop up a PDK associated with transfer print in collaboration with AIM. So again, this is where we work with foundries, and they follow our design rules, and we start to develop PDK, ADK, so you can kind of look at that system. So just one or two examples, and really this is, I can talk a little bit about this, not in too much detail, but what we have here is, you see the actual photonic package. Again, I don't have a laser pointer, but it's just this part, the kind of light green part. We're flip chipping onto that type of interposer, so it's a high density, multi-level ceramic interposer. But really, before we start the project, we're building the full system. So we're delivering the full system. And understanding of the thermals, understanding, from the top down is really important. And then you got from the bottom up. What's the chip? What's the coupling interface? What's the mode size? What type of fibers do we need to use, etc. So there's a kind of a double-pronged approach here, top down, bottom up. And you can see, for example, on the left side where we've got the photonic, this is looking at the face on. You can see the PIC with the driver, the EIC drivers on the interposer. We have solder bumps on that silver tin copper. They reflow at a particular temperature, and then the interposer, the signal is fed down through that, and then we have these bismuth thin, lower temperature reflow solder bumps. So again, you got to work out the kind of temperature sequence and the process flow. And again, we're building these systems. So as I say, it's kind of a system development. And when you start to look at that, you really understand, how your package needs to perform within the system itself. So, over the years, we've been looking at how we really can kind of set things up in a pilot line. So really the way we operate now is in Tyndall and with some of our partners, we can do low volumes. And to be honest, that in itself is a challenge because, as you've seen in the previous example, developing these, just as a matter of interest, that project takes about 2 years. So all the material sourcing takes maybe 6 to 9 months. You have a huge amount of process development, a lot of organization, and the actual packaging activity is probably around, say, 15% at a time. So it's all design, sourcing, kind of pre-testing. Packaging takes about 15%, maybe 20%. So it's quite short. Everything works, you get your materials in and you package. But it's the pre kind of development. And the challenge is people often come with their chips and say, can we have this packaged? And we kind of unravel that. It's very difficult to explain that. So getting involved and setting up design kind of protocols and getting people to be aware of that, educating them is really the only way forward because it can be very frustrating for us and for them. But that's definitely something we've learned the hard way, I will say. So the ideal scenario is that the way we work is developing kind of a process and then transferring it. So we have worked with some very large companies who are superb at manufacturing, particularly in the microelectronics domain. So we can't tell them how to manufacture and kind of manage projects. They are superb at that. What we do is do the development. We look at the machines, for example, with Photonic, we've worked on optimizing machines, and then they'll buy Photonic machines, and they'll do internal manufacturing. So that's one route to scale up. The other is with some of our partners, for example, with Fix in the Netherlands. Fix originally were Photonics. They morphed, and Fix was founded. So we work closely with Fix, that's one route to scale up. The other is then OSATs. So OSATs are very large manufacturers, and we are in discussions with some OSATs because one of the challenges they face is they really don't have the capacity to do the early development. So they need kind of partners that can do development. So that's kind of the industrial facing, the commercial facing. But really, there's an opportunity then for projects who are, maybe European, Horizon Europe, Horizon 2020, where they're looking for exploitation routes. And often, as I said, people develop designs and maybe they're not ideal for packaging, or maybe they can't be packaged at all, and they're looking for routes to maybe guide them and maybe to kind of that transition to manufacture. And I think that's one of the key things we've learned. We're good at that. We're very good at that. So it's also supporting researchers to get their research ready so that it can be scaled, and potentially giving them options to scale. And I think this is where it fits also with the European Commission's new focus on kind of a little bit lower level TRL. So that kind of research, prototyping, and then moving it to manufacture. It's not just the manufacturing. So just to give you an example, we have a project called Photonic Leap. It's under Horizon 2020. And in that, what we're developing is a glass-type low-cost package. So really, it's looking at wafer-level packaging, a ball grid array, and on a glass platform. So you can see here, for example, we're making 2 demonstrators. And this is working with IZM. So they basically can do wafer-level glass patterning and plating. So we have VIAs in there, and we have another company, LPKF. They actually structure the glass, and they can do it a very fast process. So essentially what we're trying to do here is develop up design rules. So again, with the knowledge from Photonic Leap, what we're saying is you need to come up with design rules. If we get those design rules, then we can start to promote it. We can start to tell companies about it and look at ways to manufacture it. But the project has to come up with the design rules. So in a sense, this is what the project is doing with the guidance of a pilot line. So you can see here, just very briefly, we have a silicon photonic chip. This is actually produced by IMEC, and it's got backside grating couplers and edge couplers. Joris mentioned 1 or 2 of those features. We also have an indium phosphide chip from Heinrich Hertz, and there's some details in that if you weren't aware of packaging and what pilot lines can do, you probably do the wrong things, or you may not be able to do anything at all. But the idea here is because it's a ball grid array, so it's a low cost, it's not a gold box like what these very expensive packages, and ultimately moving towards wafer level. So, you know, just as the layout, and again, we have design rules on what we can do, what we can machine in glass, via dimensions and so forth. And we started to kind of consolidate that within the project. So one example here is with SUS, now called Focuslight, a Swiss company. We're looking at out-of-plane coupling because we want to make a surface pluggable type connector. And again, that's technology that Photonic Leap has developed, kind of a pluggable optical connector from the surface. But what you see here is SUS have developed this on the far right, this quite novel micro lens. So basically, maybe I'll just run over here. What we have here is the light is coming in from the right, sorry, from the left-hand side. You have a small prism which deflects the light up, and you can barely make out on the top there's a micro lens for collimating the beam. So the idea then is that we're attaching this to the edge of the actual indium phosphide chip. You can see where the arrows are. So we can have this collimated pluggable connector. So again, and again, we have all the RF design and the different types of ORDL, the redistribution layers with vias and all. So again, these are following standardized design rules. But this particular part here, you can see we worked with Photonic where we're actually attaching the actual micro lens to the edge of the chip. And this requires that normally under solid reflow, you have very high temperatures, over 250 degrees. So epoxies tend to soften. So we had to develop this two-part epoxy process. And what you see here is we're depositing the first, what we call mechanical fixing epoxy. And then the lens is attached to the edge of that. That requires quite a bit of work. So we actually know that material. We can advise the project on what materials to use. And Photonic can develop, for example, simple things like a syringe. And here you can see the optical epoxy is attached to the back end. So we have a capillary capillary action. The liquid diffuses down between where the little gap between the backside of the lens and the actual facet itself. Another part then is looking at this is the silicon photonic one. The previous one was the indium phosphide, which is a communications device. This is a demonstrator for biomedical application. And as you can see, it's quite a complex chip. It's flip chipped, and I'll explain what we were doing there. It's got this surface, again, a pluggable type micro-optics on the top, but also we have a laser. So it's not as sophisticated as what Joris mentioned. We're actually using a hybridly integrated laser on a micro bench with micro-optics and a micro-isolator coupled to the edge of the actual chip. So this silicon photonic chip is an edge coupler. I believe it's a membrane edge coupler and a backside grating coupler. The light comes out the substrate. So what we've been doing here is we machine what we have ourselves, a CL1500. It's and just very quickly, I'll fly through this video. You can see the actual glass interposer, it's picking it up. So these are these test glass interposers, picks up the chip, brings it over, and maybe I'll speed it on a little bit. But you can see here, it's placing it on a small window. This window is designed into the machine for a laser reflow. But the problem here is that the laser, you've got these vias, so the laser is going to scatter with the vias on the glass. So we have to come up with a novel way, and I won't go into all the details because there's some complex optics switches Photonic have been working on in the head of the system. So again, that's the value of working with our partners on site. So that kind of affiliation is really, really useful. This is the Photonic device. It picks it up. And again, before we actually work with real chips, in our fabs, we have a fab in Tyndall, we can make test chips. So again, these types of reference chips, they're not functional chips, we can kind of develop the process. See, the idea is the laser will actually heat only the silicon chip. It's absorbed, so we have to choose the wavelength such that it heats up the photonic chip. So it places it then, and again, optimizing the system for reflow. So it's a localized heating type device, module. So, sorry, a little bit of a slope. Okay, then it brings it down and it bonds it. Okay, so the ultimate kind of goal here is, and one of the kind of endpoints for a successful project is that we have design rules. So, you know, when we look at this glass interposer, we need thermals, because glass, actually, people might say, well, glass is not a good thermal, you know, conductor, but it's actually quite good if you have vias. Plus, it's isolating in its horizontal direction, so heat doesn't kind of dissipate across. So there are benefits to using glass. Obviously, it's very good for RF. So coming up with these design rules, now we can start to kind of transfer that to a pilot line, such as can develop an ADK. And we're already now talking to companies who are interested in using this. And then they're not going to have to go off and develop the process with this glass material. We actually have, you know, in a sense, tried to standardize the process. So hopefully that shows you where a pilot line can help projects get organized, get structured, and focus on what's important. Coming up with design rules, not just making a demonstrator, it might have to restart, and somebody has to kind of go and make it for their application, redo it all. You can design it such that it can be kind of standard and people can interface with it much easier. So just to summarize, you know, really, you know, that kind of bridging that, what we call the valley of death between research and manufacturing, it's not necessarily high volume or even medium volume manufacturing. So that transition, co-location of industry partners is really, really valuable. So don't try and do everything yourselves. If you can get engineers on site, it's very, very useful. Transferring to industry, that's, you know, so having industry partners. Unfortunately, there's not enough packaging companies. We need more. And it may be that some of the OSATs will transition to do more photonics. Design rules are really important. It's kind of the glue that brings everything together. And more we're going to start to see this kind of more engagement with projects, and what do you tell people working on projects? What do you need to do so we can take it on? So design rules are a key part of that. Thanks.
Thanks, Peter. Questions?
Thank you for a great presentation. A quick question regarding your business model, and in particular related to IP. We heard IMEC doing a lot of spin-offs. What's your model at Tyndall? Thank you.
So when you say IP around process,
yes, process IP. And
yeah, so that's an interesting one. We do have, where we develop IP coming out of research, we'll have IP and we can license that. So we try and make it generally open access. We also want to protect it. So we're not necessarily we want to make it available to people. Some of the processes also are fairly generic, so there's not IP necessarily around that. There might be some there's more process know-how, I would say, than IP. So process know-how is something that's, you know, people won't necessarily copy. There's also material know-how, what epoxy. So for example, those material epoxies I showed, you'll be able to do it, but it takes a lot of time. So there's no IP in it, but it takes a lot of time.
Thank you.
Any other question?
Thanks, nice presentation. One question on the expanded beam interfaces. What is the mode field diameter you can expand?
It varies. So typically it goes between 50, you can make it smaller, but generally we work between, say, 50 and 100. The larger you go, the shorter the distance between that and the pluggable connector. So generally it's, say, 50 to 100. 80 is a good number, yeah.
Have you been working on the connector itself as well?
Yeah, well, so that's a good point. We've always made our own connector part. So we've had to take a fiber array and put a micro lens, but now we're talking to companies about, you know, we have projects with industry partners who are forcing the connector companies to work. That's the other benefit of working with some of the bigger companies. So the connector companies, the Senkos and these kind of companies, they can start to work on that. The challenge for them is, well, one of the benefits is you can make a molded micro lens array for the fiber ribbon for the connector part. But making that mold is quite expensive. But if they see a big value in this, they will invest in that. So yes, we've made our own, but now we're starting to work with the connector companies to make dedicated ones. Yeah.
Okay. One last question there.
And while you're waiting, the last answer to yours, you can also do 2D if it's coming from the surface. So you can make it 2D, which increases the shoreline in a sense. Yeah.
Thank you very much for the presentation. And I was just wondering, because you said there needs to be more packaging companies. And the question I have is, do you see doing more, is because the volume of packaging is high, or is there niches in packaging that are not?
Well, the big challenge is for a company is investing in packaging machines is very expensive, and they have a limited throughput. So in one sense, I think we have to move more to wafer level. So, you know, do you invest today and buy lots of machines? Because the only way you do more volume is you just, well, you scale up more machines. Or you try and get the chip on and off as quickly as you can off the machine. So that's a big investment, and that's a big roadblock for a lot of people. So, you know, that's a big challenge. I do think it's going to be made a lot easier as we go to more wafer level and it becomes more compatible with electronic style manufacturers for two reasons. It's more scalable, plus the electronic guys who already do packaging can probably do the job.
Okay, so then if I just can follow up, is that that companies that are doing packaging need to grow, or?
No, I still think we're in the dark ages with packaging. Packaging fibers to edge of chips is going to be, it's dated. It has to go. Optical interposers are the future. I firmly believe that. Optical interposer. So it's going to change packaging. So we're doing this work at the moment because we have to. Companies need it, and that's what the chips. We're provided chips, but packaging one part at a time is. You're never going to make millions of chips. You're never going to package. It's just not going to happen. And it's really, you know, it's a slow process. So for very large volumes in medical, and especially when we look at disposable type sensors and so forth, forget about it. So it really has to move towards microelectronic style packaging. So it's in a big transition.
And the microlens that you show, does it require some spot size converter or any? Does have requirements on the chip design, right? Yeah,
you need spot size converter, especially obviously for fiber. I think evanescent type flip chip, you know, I really think that holds great promise for the future.
Yeah. Thank you very much.
Okay, so let's thank Peter again. Thank you, Peter. Okay, so we have a program change. Mario Nemirovsky from Instituto Ricardo Valle, Malaga, couldn't make it. He lost flight last night. So we just give floor to Maite Bacete, next speaker from Max Linear.
Thank you. Thank you, Pascual, for inviting me. And thanks for the previous speech. I think I'm going to move to a more generalistic and like kind of more close to politics almost thing, and it's about, the presentation is not there. So while we wait for the presentation, I'm Maite Bacete, I'm president of the Valencia Silicon Cluster that we recently founded. Works? Okay. And at the same time, I'm site director of Max Linear Spain, which is based close by here in Valencia. So we wanted to take this opportunity to explain you what's this about Valencia Silicon Cluster. Maybe you have seen some news here and there on what's going on and what we are doing. We realized some years ago when all, just coming back, even in 2021, some of the microelectronics companies that were based in Valencia, just probably by chance or by the good talent that we were getting from the University Polytechnic of Valencia and the University of Valencia, there were like 4 companies focused on microelectronics based here, which was MaxLinear, Analog Devices, AMS Osram, and Bosch. All these 4 companies were having challenges to hire people. So we decided to work together and collaborate to create a small chair in the University Polytechnic called Aula of Microelectronics in order to do trainings for people. So that there is where we started to collaborate together. And then in 2021, we started with all the shortage of chips and all the CHIPS Acts around the world, right? So we also realized that there were 3 spin-offs companies in photonics that we were working separately, like microelectronics in one side and photonics in another side. And we said, okay, here is the same challenge. We are facing the same problems. We need to make this ecosystem more known at national level and regional level. And we decided to work together since 2022. We started at the end of 2021 to create this cluster. And why? Because there was such a focus of companies in this region in Valencia that was about 50% of the talent in Spain working in microelectronics and more than 60% of the photonics talent working in this sector was focused here. So we really thought that it was important to collaborate and work together in order to make this ecosystem grow. And that's when we created this Valencia Silicon Cluster formed by these 4 microelectronics companies, MaxLinear, Analog Devices, AMS, Osram, and Bosch. And then the integrated photonic companies like Ipronics, Das Photonics, now Group Oasia, and then VLC Photonics from Group Hitachi. We also have Gobernanza Industrial as one of the partners of the cluster, Digital Health Data, and of course, we work very close with the universities because, as we said, our end goal, major goal, is that we keep growing this ecosystem, and that cannot be done if we don't collaborate very close with the universities. So we have created this partnership with them in order to define all our goals and projects which are going to be our projects in the future. We will, of course, admit new members. As I said, this is very new. We officially, or let's say we created, registered the cluster just in 2023. And it will keep growing and incorporating new members, but always thinking on the focus on semiconductors, which the cluster is quite specific at national level because we are very focused on chip. All the companies that form or created this cluster are coming from the design of integrated circuits. Also, we all have a global view, like most of them, I mean, not even in Spain we have customers, some of us. Most of the customers are coming from any other country in Asia, in Europe, or in the United States. And of course, we need to focus our efforts in order to increase the talent and people with training specific in this semiconductors subjects. And it's not a problem only in Spain, it's a problem worldwide. Most of you probably are suffering the same thing. Most of us growing slower than what we would like because we cannot hire people with specific skills and train for semiconductors. So all this makes that we foresee a big project of semiconductors international campus that will put together all the agents of this ecosystem, not only those companies that we mentioned in microelectronics and also photonics, but also, of course, the universities, the research centers, the pilot fabs that we are starting to develop or have been developing in the last years, but need still to grow and to keep having investments to evolve, right? And also, of course, the companies that are using the chips, because there is a lot of skills that needs to be developed, and we really foresee that we need to work closer to the end users to keep growing this market and keep helping those companies to use the chips that we develop. And at the same time, work with some of the driving semiconductors companies that will help to increase this ecosystem and will be like the driving actors of this sector. This is just kind of a photo showing this strategy of the cluster. We focused, our founders are focused on IC development, and from there we will be adding all other agents of the ecosystem. So we promoted, and it was approved in February last year, kind of what is called here a PNL, project known for law, which supports our plan of the campus semiconductors international campus. And we are working close to the authorities in order to make this a reality. Our mission is to create this talent, as I said, and connect this talent with all the agents of the ecosystem. And it's going to be key that it's not only a regional level, not a national level, it needs to be an international level. And we foresee that this campus will grow, and we want to be seen in the at national level and international as a strong ecosystem in this region. One of the first steps that have been approved, and it's very important for our objectives, is that we have got 3 chairs approved by the PERTE of chips that Guillermo was explaining before. It's about 13 million of funding from the Spanish authority, which is huge. Those 3 ones are focused in the region in Valencia, and 2 of them are done in collaboration with the University Polytechnic. In fact, the ones that are getting the grants are the universities. The two are from the University Polytechnic of Valencia, and 1 is from the University of Valencia. The good thing is that all these have been done with very close collaboration with the companies in the Valencia Silicon Cluster, and each one is specializing in one different thing, right? So in the University Polytechnic of Valencia, we have 1 focused in microelectronics and another 1 focused on photonics. Tomorrow you will have a session, the session 4 at the end. Pascual and Jose will explain in more detail what's about the photonics chair approved in the University Polytechnic. And we have another one in the University of Valencia that has been also approved, and it's going to be more focused on materials to be used in the semiconductors industry and also microelectronics. It's going to incorporate new master's degrees, new doctorates and research projects focused on these areas. And the important thing to highlight is also that not only these 30 million of fundings from the Spanish government, apart from this, the industry is putting 2 million euros in this region to be able to do these 3 chairs. So I think this is going to be a big milestone for the future, and hope that in some years from now we foresee that the results are very good, and we are really obtaining our goal of making this ecosystem bigger and get more talent and more research centers and more infrastructures on this sector, right? It will not pass from there. So the last idea I wanted to highlight, this is the first rocks of this International Semiconductors Campus. In the future, more projects will be added to this idea of the campus, and all will be done in collaboration of the different companies in the sector, plus the universities, of course the authorities, and research centers that are based here, as well as we expect new investments coming to the region and adding value to this idea of the Semiconductors International Campus. And I think that's it from my side.
Thanks, Maite, for the presentation. As you see, we are a bit ahead of time, but I think that is always okay. So, questions for Maite, please?
It's coffee time, so they can put the questions on the coffee.
I'll make one. What is exactly the involvement of the regional government on the cluster?
Good question. We are working a lot with them since the beginning. It's true that with the change of the government, the regional government, it's like we are almost starting from the beginning to teach them. And you know, because you have experienced it, this is not an easy sector, right? It's not an easy ecosystem to understand how it works and the international application of this sector. So far, the current regional government is involved in a European program on semiconductors. As soon as they arrived to the government, they tried to join this that was already in place, and they joined in September. So they are very interested. They approved this PNL. We still have a lot of work to do with together with them, but I think they start to see this as a strategic market and and sector, and they want to work with us in order to put in place and help on these projects, right?
Thank you, Maite. Any question from the audience? Everyone is wanting for coffee? Okay, so then we close the session. Thank you very much. Thanks all the speakers again.
Hello, everyone. Okay, so thanks everyone for being on time after the coffee break. I know it's always difficult. I'm Íñigo Artundo from VLC Photonics. Pascual asked me to moderate this session. So the next session is going to be mostly dealing with the R&D projects that were approved in the recent call by CEDETI on this Misiones chip call that was also part of this bigger framework on the semiconductor PERTE. And we have 4 interesting presentations now. We'll be starting with the first one by Jonas Lauerman, who is the CEO of Bioherent, a spin-off company from the University of Malaga that will be introducing the research and work they do also on photonic biosensing. Jonas, the floor is yours.
Thank you very much for the introduction, and thanks for inviting me to give this talk. So, let me introduce myself first. So I'm, even though I'm one of the founders of a very Andalusian company, I'm actually from Germany. I did my bachelor and master degree in electrical engineering, information technology, and computer science at the Rheinisch-Westfälische Technische Hochschule Aachen, where I had my first contact with photonics in my master thesis, where I worked on the Pix for Life project for the development of a multicolor laser engine. Later, I went to Malaga to do my PhD in telecommunications, where I joined the Photonics and RF laboratory led by Professor Inigo Molina Fernandez. And then after that, based on the technology we researched during my PhD thesis, we founded Bioherent, where I'm currently working as director and also head of engineering. So the Misiones chip project we have, or we got in the last year, is actually called Research for the Integration of Novel Multiplexed Photonic and Hyperspectral Terahertz Sensing Architectures in a Microfluidic In Vitro System for Monitoring Cancer Drug Treatments. So in short, Impact Photonics, which started in the last year in September. It's going to end in August 2025. And during this talk, I want to give questions to the following 3 questions, which is, what are the objectives of this Impact Photonics project? Who are the participants? And also, what is our strategy? So maybe starting with the second question, who are the participants? Starting with Bioherent. Bioherent is the startup of 3 different research groups from the University of Malaga, from the Photonics and RF Research Lab, the Biomimetic Dendrimer Laboratory Chemistry Group, and the Allergic Disease Research Lab. With the investment from Bullner Capital and the Invierte CEDETI, we got a funding from in the height of 3 million euros. And we started at the October of 2021 with 1 employee. And at the end of December 2023, we already got 16 employees. So with 8 of the employees with a background in engineering, 5 with a background in chemistry, immunology, and of course 3 with a background more in administrative matters. So the mission for Bioherent is to provide technology or highly sensitive photonic integrated sensing technology for in vitro diagnostic applications. Firstly, targeting the application of drug allergies. Then we have another key player, which is microliquid. Microliquid is forming part of TE Connectivity. So TE Connectivity is a global industrial leader in sensor solutions with around 80,000 employees. I think 150 with customers in more than 150 countries. And offering solutions in industrial, medical technology, energy, data communications. And recently in 2021, they wanted to increase their portfolio in the in vitro diagnostic section in the application for point of care and microfluidics. So that's why they bought 3 different companies worldwide in the States and in Europe. One of those is Microliquid, and Microliquid is a Basque country-based company founded in 2008, which is focusing on the prototyping and mass fabrication of microfluidic devices. Then we have ATG Therapeutics. So ATG Therapeutics is a spin-off of 2 oncology institutes here in Spain, and its mission is providing information for the personalized cancer treatment. So how are they doing this? They want to monitor the resistance reaction of the patients for cancer treatments. So how they're doing this, they identify the relevant biomarkers for those treatments to see if the treatment is effective and efficient. So if they see, for example, that certain biomarkers are appearing in the system of the patient, then they can tell, okay, this treatment is not effective anymore, you have to change the treatment. And that's a very useful information for personalized medicine. Another company is MacWinds, which is similar to Bioherent, providing a quantitative, ultrasensitive, multiplexed immunoassay platform, which was, MacWinds was founded by 2 professors from the CSIC in Madrid, and it already has around 20 people, ranging from physicists to chemists to engineers with a high expertise in surface functionalization techniques. Another company participant is LeapWave. LeapWave is a spin-off founded in 2022 from the University Carlos III in Madrid, providing technology in the radio frequency millimeter range to sub-millimeter wavelength range for applications in instrumentation, for example, wafer level testing, communications for ultra-wide bandwidth, interconnections, non-destructive analysis, which is essentially the case here for the project, where you have a contactless measurement. Then also semiconductor assembly and packaging, trying to fuse photonics and RF interconnects. Then, of course, we have AG Photonics. AG Photonics is also a spin-off from the University of Malaga, from the RF and Photonics and RF Research Lab in Malaga. AG Photonics is a pure photonics company, you could say, with a high expertise in coherent receivers, passive devices based on sub-wavelengths, gratings, metamaterials, and also input-output chip coupling, especially optical phased arrays for creating highly collimated beams. And the mission from AG Photonics is facilitating the access of wireless optical communication systems by integrating transceivers into the chips. I think tomorrow there's also a talk from AG Photonics during the day if you have more interest in this. Of course, this is not only a project with, let's say, private institutions, but also with public collaborations. Within this collaboration, Biohino will collaborate with the University of Malaga, with the Photonics and RF Research Lab. Microliquid is going to collaborate with the university in the Basque country, the microfluidics cluster. ATG is going to collaborate with IDIBEL and IBIMA, Plataforma Bionant. MacWinds is going to collaborate with the university in Catalonia, with the Innovation in Materials and Molecular Group. LeapWave is going to collaborate with the University Carlos III, with the Optoelectronic and Laser Technology Group, And AG Photonics is also like by here collaborating with the Photonics and REF research group. So, what are the objectives of this project? So, maybe there's one last objective, or the last target objective where all the small objectives are targeting to, which is the application, the simultaneous monitoring of biomarkers related to cancer drug treatments. So this has several sub-objectives. But we're talking here at 5 different biomarkers for the detection, okay? Which is rituximab and bevacizumab, which are both drugs, which are monoclonal antibody medication for the for cancer drug treatments. And then there's also the ATG AngioDx predicts, okay, not working, predict, which is a biomarker for telling how efficient and effective is the treatment with those drugs. Okay, and then also we have the IgE and IgG anti-drug antibodies. Those are antibodies produced by the patient which diminish the effectiveness of those drugs. So monitoring all those different biomarkers in the system of a patient gives information about how effective the treatment actually is, or if the treatment has to be changed. Then we have, of course, one of the sub objectives is the microfluidic cartridge integration. So typically when you have a biosensing system, you have a cartridge and also, let's say, a bigger microfluidic base. We have a manifold integrated, and this manifold is treating different liquids and injecting different liquids into the cartridge. So what we want to achieve here is to have a cartridge where most of the microfluidic functionality is integrated in one cartridge. And we want to have several independent microfluidic channels. This sounds a little bit unnecessary, but it's very necessary if we're talking about different immunoassays, because each biomarker can have a different immunoassay. So you need to control the immunoassay above this for each biomarker independently. We want also have a cartridge which can work with complex samples. So we're talking about not only prepared samples in milliQ or PBS, but we're talking about serum, plasma, or even blood. And of course, this microfluidic cartridge is integrating the photonic sensing chip. And we also want to integrate an interface for the terahertz sensor. Then we have another objective, which is the layer discriminating photonic sensing architecture. Essentially, the layer discriminating photonic sensing architecture is permitting the propagation of several independent modes within the sensing structure. And why do you want to do this? We can actually later, by detecting the different modes, you can actually differentiate where the phase change is coming from. If it's coming from the bulk, if it's coming from the surface of the sensor, or if it's coming from thermal fluctuations. So we have less signal falsification due to thermal influences or other influences. Maybe just a quick recap how this works. So I'm going to talk a little bit how integrated photonic biosensing in general is working. You have your silicon wafer on which you have your silicon dioxide and silicon, your waveguide layer, in our case silicon nitride. And to make this a biosensor, you have typically this waveguide exposed to your liquid provided, for example, by the cartridge. And within this waveguide, you have your optical mode propagating. And this mode has an evanescence field tail, which is penetrating the water or the liquid around it. And of course, any change in refractive index within this evanescence field tail is going to give a change in the phase. Assuming there's no refractive index change, then you have a constant phase of this mode after propagating a certain length. If there are any changes in this region, you're going to alter this phase. So to make this a biosensor, instead of just a refractive index sensor, you have to give the waveguide a biorecognition layer, which makes it sensitive to only one target molecule. So, for example, if you functionalize your waveguide with a certain antibody and then you inject the antigen to it, and you have the chance of the antigen attaching to the surface, you're altering the refractive index, And of course, this will change the phase of the light propagating. So if you have an interference sensor, you typically have an Marcinder interferometer, where you have your sensing waveguide and your reference waveguide, and then you have typically a Y junction, where you have your interference signal and your phase, or the change in refractive index is linear correlated to the phase, and the phase change is then transferred into an intensity variation. But of course, you don't have to do this with two different waveguides. You can actually use one multimode waveguide, for example, with vertical and lateral and horizontal modes, which was investigated by Professor Lechuga and also by Professor Garcia Perez. So that's nothing new. What we want to do is use dual polarization or bimodal coherent sensing. So we are going to use, for example, the TE, the TM mode, in both in sensing and reference waveguide, and make, let's say, a double coherent detection, where we detect just the TE mode and just the TM mode. Or, for example, using the same polarization but two different modes, for example, T0, T1, in sensing and reference waveguide, and then detect the two coherent signals from those modes. And this enables us to tell if the signal change we observe is actually coming from the surface or not. Okay, on the other side, we also have to improve our reading system and increase the capability of multiplexing. So that's one of the things we are going to work on in this project. We want to integrate more sensing units on the chip. We want to improve the on-chips coupling structures, and we want to improve, of course, the optoelectronic detection system. On the other side, we're going to introduce a new kind of sensor, which is going to be a terahertz reflectometer architecture, which is going to add complementary information to the photonic sensing information. This measurement is a contactless measurement, so let's say the transmitting structure is not actually in the cartridge, but is in the instrument, and gives us a spectral measurement to the photonic sensing signal. So how's this working? So you have two lasers with different wavelengths, which you are combining with a mixer, and then inserting into a 3 dB splitter. Then part of the light is going to a monitor directly, and part of the light is going to a sample. This sample is then going to reflect the incoming signal, and this reflectance is going to be guided then to a receiver. And then this information will be analyzed with together with the photonic sensing signal. I'm sorry. So, of course, there are also, let's say, chemical objectives, because we need actually detect 5 different biomarkers, and we have to anchor the bioreceptors or biomarkers onto the sensing waveguides. So that is one objective. The other objective is also to control the orientation of those biomolecules on top of the surface, because many times you have difficulties to orientate the biomarker in the correct position. And by helping or by maximizing those orientation to the optimum, you can actually increase sensitivity. Then, of course, we want to have a signal. We want to have a chip where you can detect the 5 biomarkers at the same time. So we want to have a multiplexed biorecognition layer. So that means we want to functionalize each biosensor individually. Then, of course, all those objectives are going to end in the proof of concept objective, which is demonstrating that all those concepts are working together of course, with model samples, but also with patient samples. And then compare all those results with the golden standard for those biomarkers, which is essentially the ELISA. So that's it. And so if you have any questions, please keep in mind that I'm not an expert in many of those concepts I presented. So don't expect me to give correct answers on all the topics, okay?
Are there any questions here? Please, Michael.
Yeah. I have no clue.
Thanks. Fascinating. One question, and perhaps it's outside of the domain that you cover. But you mentioned also wanting to use terahertz for, well, complementary sensing.
Yeah.
I saw on the plot that your terahertz radiation, so you generate it by beating two lasers.
Yes.
And then you saw on the plot it goes up to like 300 gigahertz.
Yeah, more around this, yeah.
Have you looked at other ways to generate terahertz instead of the beating of two lasers?
No, because this is a part of Leap Wave. So I'm not expert in terahertz sending. So, but I think there's Guillermo is here from Leap Wave who could comment on this maybe later after the. If you want to answer this question, we can probably talk later about this.
Thank you. We have another question here. Carlos.
Thank you, Jonas, for the presentation. Only a short question. What kind of wavelength or what range of wavelength do you use for the interferometer part of the photonic device?
Okay, in this project, okay. We're going to use 1,310 nanometers.
Any other question? Guillermo, maybe you can.
Yeah, I can take the question on the terahertz if you want to have an advance. We've looked at many ways. I don't know if you want to ask about electronic or photonic. We are basically interested in the photonic because we want continuous tuning. And that's why we use the two lasers. What is novel is that we are developing an integrated substrate for terahertz, which allows to use the same principle that Jonas explained about the evanescent wave, but instead of, so we use the same structure for sensing. And to have continuous tuning from a few gigahertz up to 3, we are pretty confident that we can reach even 1 terahertz. It's all integrated, and it's only by optical heterodynamics that we can cover this entire range.
Another question. Have you considered the possibility of working in the mid-infrared instead of working in the terahertz range or in the near-infrared?
Not yet, no.
What do you think about that? Would be feasible, taking into account the technology?
I mean, there would be a major technology transfer regarding the coherent detection system, if we're talking about the interferometric system, right?
In general, as you know, the mid-infrared fits with the absorption of many molecules and so on, so perhaps it would be more effective I think when you are trying to detect molecules or whatever.
Okay, what we want to do is detect certain biomarkers, and typically those biomarkers, it's not that relevant to detect them in, let's say, in a spectrum. The advantage for the interferometric sensor is that it's very sensitive. So that's one advantage of the system, maintaining it close to the, let's say, near infrared or in the visible spectrum. I think the mid-infrared is very useful if you want to detect some, let's say, molecules in gases or gas sensor. then it's becoming more relevant going into the mid-infrared. But I think for biodetection, if you want to detect certain biomarkers, the trend is going more to the visible than to the mid-infrared.
Okay, thank you.
Okay, so if there are no other questions, please let's thank Jonas once again. And let's move to the next presentation by Francisco Cruz, Product Manager and R&D Engineer for Photonics from Technobit. Yeah, please. So, Francisco, the floor is yours. Thanks a lot.
Hello, good morning. Thank you very much to invite me to provide you an overview of what we are doing in OSIA regarding the Mission Experte chip. We are working within the context of the Mission Experte chip in different technologies, let's say. We are working mainly in single photon sources. We are working also in single photon detectors, QKID transceivers, also lithium niobate modulators, microwave photonics, intended to electronic warfare and radars, and metasurfaces for low observability for military platforms. But today I'm going to focus on two main areas. One of them is single photon sources based on 3-5 semiconductor quantum dots. As you know, one of the problems with the current QKID transceiver deployed in the market, most of them, if not all, are based on what we call weak coherent pulses. That means strong attenuated pulse lasers. But how should the photon source be for quantum communication? First of all, we are looking for purity. I mean, we are looking to emit one photon and only one photon. We are also looking for brightness. We are also looking for indistinguished photon and deterministic emission. As I commented previously, the most extended way to provide photon sources for the QKID commercially deployed in the market are based in strongly attenuated lasers. But the problem with this kind of sources is that they have a Poissonian emission. That means that you cannot guarantee that you emit one photon and only one photon at a time. So in some times you can emit one photon, but in other times you can emit two or more photons. This has a negative impact on security and in the secure key rate that we can achieve with this kind of sources. Of course, you can use decoy states, but this not, at the end, you can find ways to hack even this kind of decoy state due to problems with the intensity of the laser. So at the end, what we are looking is true single photon sources. If we analyze the different technological possibilities to provide this kind of single photon sources, of course, we have the parametric down conversion, the four-way missing, nitrogen vacancy centers, and quantum dots. If we compare the performance of the key performance indicator of these different kind of technologies, at the end we can reach at the conclusion that the quantum dots, the semiconductor quantum dots, are the closer to the ideal, let's say, single photon source. Well, as you know, with the quantum dots, we have a semiconductor nanostructure, which is confined in 3D dimensions in such a way that when the exciton, which is confined in this nanostructure, is excited, we can emit one photon and only one photon at a time. Because of that, we are working in this kind of technology in order to provide commercial true single photon sources. We are working with 3.5 semiconductor quantum dots, mainly indium phosphide and also gallium nitride. Of course, if you compare, because this is important, why we are using this kind of 3.5 semiconductor quantum dots, if you compare the different performance of the, for example, indium phosphide and gallium nitride, one of the key advantage regarding gallium nitride and in general 3 nitrides family is that they can emit this single photon at room temperature. When we are using indium phosphide or gallium arsenide families, we need a strong cooling system to provide this kind of emission. However, with gallium nitride, we can produce this kind of single photon at room temperature. So we have to analyze a trade-off between the different possibilities of the different materials. As I commented previously, with arsenide and phosphide quantum dots, we can achieve high purity, high brightness, high indistinguished photon, of course, deterministic emission, but the main handicap is we need low operating temperature and strong cooling. On the other hand, with the 3 nitrides quantum dots, we achieve moderate purity, moderate brightness. Of course, they are deterministic. They can work with high operating temperature, but we cannot produce undistinguished photon. So depending on the quantum application or general the application, we have to evaluate which is more suitable in each case, depending on the application. In addition to that, we are working also to encapsulate this kind of quantum dots in a nanocavity. Nanocavity, let's say micropilar, nanowire or something similar, because encapsulating the quantum dot within this nanocavity, we can improve the photon extraction. We can also improve the emission speed, the efficiency, the single photon purity, this is also very important, and even we can improve the indistinguishability of these emitted photons. Another interesting point is how to excite the quantum dots. We can excite optically or we can excite electrically. We want to provide, let's say, application that can be easily used by the users, and traditionally this kind of quantum dots has been optically excited. But from a practical point of view, if we want to provide to the market some practical single photon source, it is preferred to use electrical excitation, and we are working also in provide this kind of electrical excitation by including two PIN structure adjacent in order to convert the classical light into quantum light. Regarding manufacturing, we are also working in a 3.5 pilot line, which is going to be installed in the facilities of University Polytechnic of Valencia, in order to provide the manufacturing of this kind of quantum dots. The other thing that we are working with the Mission Experte chip is to provide a hybrid photonic platform for QKD peak. Of course, if we analyze the different photonic platforms we currently use for different applications, and if we analyze the kind of components that we need to implement discrete variable or continuous variable QKD, of course, we can compare the different kind of components, the different kind of photonic platform that can be used to implement these components. We reach to the conclusion, let's say that we cannot use one single photonic platform to implement optimally all of kind of photonic devices that we need for a QKD transceiver. Because of that, we are working in a hybrid photonic platform in order to combine 3.5 with silicon photonics, mainly silicon nitride, in order to combine, let's say, the best of both worlds. We are working in different ways of combine this kind of different photonic platform materials, and one of the ways that we are exploring is the microtransfer printing. And that's all. If you want any question, I'm open.
Do you have any questions?
Hi, thank you for the nice presentations. My question is about the active materials, so the quantum dots. Sorry. Have you contemplated using coherent quantum dots instead of semiconductor ones for the single photon sources?
Yes, but we prefer a solid state, let's say, platform in order to be more easily integrated in a, let's say, traditional system. And we think that maybe the semiconductor quantum dots could be more suitable. But yes, we explore this possibility, yes. Mm-hmm.
Thank you very much for the presentation, especially the 3D small films. I would like to ask you about if there is a need of any temperature control.
Could you repeat, please?
Temperature control.
Yes. Mainly when we are working with indium phosphide or gallium arsenide, we need a strong temperature control. Because of that, we were also exploring the possibility to use gallium nitride, because in this case, of course, we need to control the temperature, but with gallium nitride, we can produce this single photon with not only room temperature, even with higher temperature. But on the other hand, we cannot produce undistinguished photon, and this is a handicap for some kind of quantum application where we are focused this kind of system. So the response is yes. Mm-hmm.
What is the status of your development in comparison with other developments all over the world in this subject?
Yes, currently there are other groups. We are working in the design of single photon source based on quantum dots. But if you review the bibliography, you can find that most of these groups are working in the first optical window. The idea of this project is to work to emit single photon in the third optical window. So this is of the challenge. Of course, it's a challenge, but this is one of the main, let's say, innovative points of this proposal.
Thank you.
Any other question? We are way ahead of schedule, so I'll also make another question, if you don't mind.
Of course.
So, what are the challenges that you envision for the hybrid integration part? Being able to combine indium phosphide with silicon nitride material versus the more traditional silicon one? And also, what are the challenges associated to the use of microtransfer printing versus more conventional techniques like flip chip?
Yes. Regarding the last question, of course, microtransfer printing is very challenging. It's very complicated, let's say, to find the right point. And regarding the combination of different technologies, of course, it's also a challenge. But as you know, in Spain, we are trying within the partnership to deploy a 3.5 foundry. We have a very well-established silicon photonics foundry. And I think that there is room to implement, let's say, this hybrid heterogeneous photonic platform, because I think that there are compelling arguments in order to carry out this effort to implement this technology in Spain, to combine this platform not only for quantum application, that is our main focus, but also, say, for classical application. So yes, the response is yes. This is very challenging for the combination of the different platforms, for the way of combining this kind of platform, but we think that it deserves the effort to carry out this way.
Thank you. And do you envision to open maybe this platform to external users in a foundry service?
At the end, the target, let's say, as you know, the target of the mission expert chief is low TRL. So I think that it is not time to think of this time, but maybe, why not?
Yeah, let's hope for it. Okay, let's thank Francisco once more, please. Thank you. And we move to the third presentation of this session by Hiptronics, Santos Martin here. Thank you, Santos, the floor is yours.
Okay, thank you. I'm Santos Martin from Hiptronics. I'm going to present to you the program that we have received in the consortium, what we try to do, the goals we want to achieve, and a comparison with the state of the art of encapsulation up to now. So the aim of this project is a research and development on smart chips free of rare earths, together with new additional manufacturing processes, 3D printing. And of course, also the equipment, and equipment, when we talk about 3D, is equipment plus all the informatics and programs that make it possible. This aim has three strategic objectives. First, eliminate tensions associated with dependencies on rare earths. As you know, there is a listing published by the European Commission regarding rare materials that we try to avoid as much as possible, or to delete of the devices we want to develop. New manufacturing techniques based on additive manufacturing, 3D printing, that makes it possible to manufacture in a single step. And third, development of smart chips that may provide additional and different values in strategic sectors. In three sectors we are going to concentrate: health, consumer, luminaries, and telecommunications. Maybe luminaries are not a very chic sector, but according to the US Department of Energy, the consumption of lighting in cities is 50% in year 22, 50% of the consumption of power energy in the US, and it's expected that in 2050 it will be more than double. The participants, we are 8 companies in the consortium, and we have the experience to cover from the chip design up to the packaging and final manufacturing, including the demonstrators. We are supporting We are supported by 3 entities, technological centers, Idonial, SAID, ICA4, and CD6 UPC. The activities in the project are going, because we were awarded that in the last quarter of last year. Design of light emitting optoelectronic chips with versatile spectral characteristics. When we talk about chips, chips could be either the less emitter alone, or the device including several chips inside and totally encapsulated with a lens. R&D of new deposition process for thermoplastic, I repeat, thermoplastic materials with different optical functionalities. And the third, design and development of demonstrator to validate the process and to show the reality of the product. The research, we will start regarding materials. Then what we are going to try is white light that imitates the emitted by the sun. In red light, with a spectral bandwidth of about 100 nanometers for biotechnological applications. I mean, a sensor of blood coagulation. This type of sensor was started a long time ago, in 2014, by the British Army for the troops in Afghanistan. Oh, excuse me. And later on, they were for the National Health System of UK. These were based on resonant devices who have they work, let's say, quite well, but they have the handicap that they use an expendable device. And it was, let's say, not cheap. And finally, a monochromatic infrared light with below 5 nanometers bandwidth and spectrally stable. This is an example of photonic chip. This has, let's say, nothing to do with the chips you are going to design or to develop for this project, but provides you an idea about what we are talking about. This is a typical photonic chip. You have a metal frame over which they are assembled different electronics, in this case LID, driver or signal processor, finally an encapsulation, and the bending of the LED frame. The base of the electronics device will be made with the following parts. A chip with photonic monochromatic light emitters, solid-state emission diodes, located on an ultraviolet blue wafer for generation of white light. This will be used for luminaries and also solid-state emission diodes with DR red for the medical health applications. These emitting diodes will be integrated in a chip with corresponding, with corresponding connection and associated microelectronics. Below you can see photographs, one example of this. You may see LID and also a signal processor integrated on that on a metal frame with wire bondings, 25 microns diameters for making the connections. This is also an example of that, an enlarged photograph of it. You may see that the LED are placed on a metallized ceramic because anodes and cathodes are in the same surface, so this provides electrical isolation to the metal frame. Once you have, let's say, the chips located in the metal frame, the thermoplastic will be deposited on the chip in the bottom side of the chip to make the support for the advanced optics that will be also deposited by 3D printing and to manufacture the optics. As I have mentioned before, we have to develop chips to make white lights because most of the market for white light, they are using solid-state blue an ultraviolet diode with a wafer with different spectral converters. These spectral converters, they use rare earths. Our goal and one of the aims of this project is to delete, to remove these rare earths and use luminescent organic materials. These ones would not be part of the LED itself, but will be integrated inside the optics through 3D printing. The same will be done with the red light LIDs that, as I mentioned, will be for health application. The spectral band we're going to cover is 600 nanometers up to 700 nanometers. As I mentioned before, both cases, these spectral converters will be deposited on the thermoplastic optics, separate from the leaf. This has the advantage to avoid overheating and degradation of the chip. Then, once we have seen materials and names of this material we're going to use, then is the encapsulation. The encapsulation, up to a state of the encapsulation is injection molding. We are going to replace by thermoplastic using 3D printing. Thermoplastic is also used in injection molding. Although I know that some of you are a little bit skeptical on that, but it is proved and done. So, I would like you to see in these two photographs the lens, which is over the LED, with the wire bonding connecting the LED with the rest of the element. And then there will be a last element, will be the optical multiplexer 5-to-1 for laser pumping. Our idea is to investigate the volume Bragg grating to block the wavelength of laser bars with emission around 780 nanometers. Our idea is to make a device with a stack of 19 laser separated 1.5 nanometers to use them as a single emitting source. Well, the additive manufacturing process, or in other words, the 3D printing, we have to first investigate and develop the tools, including all the programs for that, and the equipment to perform it. Once that, thermoplastic will be used because we have seen it's better than thermosettings, and the optical and photonic properties of the crystalline state for us is well proof. Use thermoplastics will allow us to face the following three challenges. Deposition with control drop volume in order to deposit layer with a specific thickness. As you know, the thickness, the accuracy of thickness is a critical parameter for spectral converters. Also, deposition in a variable range of temperatures. For thermoplastic, you have to use more than 300 degrees Celsius, and then cool it below 300 to form the lens. This is going to be one of the basic differences between the actual injection molding and 3D printing. In that case, for this 3D printing, we're going to use a patent from QPO in 2022 to adapt to this 3D printing. And then the last one, the multi-material deposition in layers to be able to manufacture the light-emitting optoelectronic device. When I mean device, I mean the full device, not the chip itself, in a single process. And finally, we have to manufacture the demonstrator in order to validate and to show the result we have obtained. The demonstrator will be the coagulation time and analysis system that sends the results through a mobile device to a control center. The second, the luminaries, white luminary on highlighting quality, and luminary with adaptable monochromatic emission in the red band. And finally, the fiber optic copper laser, the stack of 19. This is what we do, what we pretend to do, or we will try to do, which is the actual state of the art to manufacture some kind of these devices. This is not 3D printing. This is, let's say, the baseline. Oh, sorry. The basic state of the art on this chip manufacturing. First, you have die attach with a curing for the glues that you have used during the attach and bonding. This bonding can be made either gold or aluminum, wedge bonding or ball bonding. For our point of view, up to now, we have always used aluminum. First, it's cheaper. Second, as far as the degradation of the signal compared with gold, it has not been so important. And the process, the wedge bonding, it has been enough for this type of devices. Once you have that, then you have to separate the different devices on the metal frame. Once you have separate, you have to go to injection machine, make the molding. In this case, we made the molding with thermoplastic for mold with 4 cavities, no problem. And then after that, we make the optical and functional test of the final device. And once the final device is tested, then you make the cutting of the pins and separation and conforming of the pins. This is an example of the actual state of the art, non-3D printing. You may see on the left the die attach bonding, and on the right the bonder. In this case is aluminum wedge bonding. This is the high power laser to separate the metal frames of the different devices, and and the injection machine we use in an ambient of nitrogen for the 4 cavity mold. This is the last part of this manufacturing process, in which they make the cutting, bend, and test of the device. That's as far as machines are concerned. These are as far as the building process of this device. Not, I repeat, not this is the baseline, but not the device that or the devices, researches, and to be developed in the PERTE. First, you have the metal frame. In this metal frame, you assemble the different electronics. In this case, LED and signal processor. You may see the wire bondings. Well, the LED over, as I mentioned before, on a ceramic to make the isolation of both. This is the result of the injection of on one device. This is the lens formed over the LID. This is our photographs of the semi-finest device. You may see some details of the bonding and on the electronic inside, and the lens just over the LED. These are the final devices, and that's all. Thanks for your attention on behalf of the project team. So I don't know if I have been very fast, but please, any question?
Thanks a lot. Is there any question for Santos?
Thank you very much, Santos, for the presentation. I have only one question about production.
About?
Production. How many units can you produce if the packaging line is finished, or when the packaging line will be finished?
Well, the baseline with the machines I have shown you there is between 250,000 and 300,000 per year. That's the current rate of this line. This line making doubling of two different machines. It is possible to upgrade up to maximum 2 million. No more.
And the precision that you need to put the LED on the metal frame?
No, the LED is assembled over a ceramic, because the anodes and cathodes are not in the same surface of the LED. One is in the top and the other is in the bottom. Because of the metal frame, you cannot. If you place directly on the metal frame, you make a short circuit. So the ceramic provides the isolation. Ceramic is metallized on the top part, and then.
But that. Here.
Well, you may see there the yellow rectangle. This is the metallized part of the ceramic. The LED is assembled on the ceramic, and you may see one wire connecting the LED directly to the metal frame, and the second on the ceramics, which is making the second connection on the LED to other parts of the pin of the metal frame.
And the precision that you put the precision that you obtain putting the LED into the metal frame is around 10 microns, 5 microns?
The thickness of the metal frame?
No, the precision on site.
5 microns.
5 microns.
Well, excuse me. Depending on the application, I mean, what precise this lens, maybe one of the people here, Carlos may provide more information. This lens is self-corrected, the sun pitch deviation on that. So depending on, but they have, of course, the tolerance. Depending on the precision you want to reach, and that depends on what kind of device you want to perform there. The maximum pitch deviation would be 5 microns. These machines are prepared up to 0.3 microns. In other words, 300 nanometers.
So usually you work in visible light, no? Visual frequencies. Do you know the performance of these thermoplastics in telecom bands?
No, we have not been tested that. Where you mean silicon band?
Sorry?
You mean what band?
The telecom band is 1.5, for example, 1.3.
Well, this device, the device I have presented to you, this is a fiber optic translator for fiber optics.
Okay.
So.
So it works.
Now, I have a question myself. You mentioned in this slide specifically that you will be using some spectral converters based on organic materials.
Yes.
Will these converters will be some kind of coating that you spray on top of the thermo-optic plastic, or?
That's the intention. That's going to be one of the points, the key points of this research. So what is clear is that this has to be separated from the lens. Then how we are going to integrate in the thermoplastic when they make the 3D lens forming.
This is one of the things that we are working on. I will be pleased to present our solution once we finish that. I mean,
Okay.
As I mentioned before, we were awarded, all the consortium, last quarter of last year, and we had not finished. It's a 2-year work, but we are quite confident we will achieve the goals.
You mentioned also the difference between thermoptic plastics compared to 3D printing, I guess for the micro lenses.
Thermoplastic is the material. How you make the forming of the lens or the encapsulation, either injection or 3D, at the end, the problem of thermoplastic, we prefer thermoplastic. We have seen they have no degradation, they have no, let's say, this yellow appearance through the years. And thermoplastic, we have experience in injection molding without any problems. So the deposition in 3D, we do not expect to have any problems too. We think it should be easier. Why? Because in injection molding, you have to make the injection more than 300 Celsius degrees, and then you have to cool to form the lens below 300. We expect with 3D to avoid this problem.
So you're actually considering doing 3D printing of the...
Yes.
Yeah, okay.
No, that is one of the goals. I mean, the encapsulation includes, apart from this device, you have seen encapsulation, which is all this plastic, let's say, housing, transparent housing, with the lens on it. This is now in injection made in one step. In 3D, we plan, as I mentioned before, maybe it was not very clear, to make first on the device, because at the end the device should have some kind of substrate, either metal or ceramics, depending on the application. The bottom part, in which the optical is not considered, also with 3D, and then to form the other part of the, let's say, the top part, including the optics and the grating for the LEDs with 3D too.
Okay, clear. Okay, thank you. Any other question? Okay, if not, let's thank Santos once again. So the last speaker of the session will be Jorge Blasco, which is the Technical Director of Photonic Sense. Jorge, the floor is yours. Thank you.
Thank you very much. Well, first of all, thank you very much to Pascual and to UPV Fab for inviting and giving me the opportunity to speak about our technology and our company. Let's start telling that we are a company with a single product line, that it's a camera that produces in a single shot at 30 frames per second, both the red, green and blue image and the depth map at the same time. And we are unique in that. We're based on the other side of the city, near the airport, here in Valencia. We have a couple of employees in Tokyo, a small sales office, another person in Taiwan, and distributors in all the major Chinese cities and in Los Gatos, California. Basically, as I told and I repeat, we are the unique company in the world delivering image and depth at 30 frames per second. And we have some other competitive advantages that I will tell you in a minute. An important factor is that we have also a disruptive manufacturing process that I will speak about it in a minute. And we have 12 and a half patents. I tell 12 and a half, same as the pilot Angel Nieto, that was 12 and a half times champion of the world, even if I'm not superstitious of the 13th. These are our products. One of them is this small camera that you see in my hand. You nearly don't see it because it's a small form factor to be injected in mobile phones and tablets. Our first tablet customer put inside this tablet an Android tablet that we developed together with Qualcomm. So it's the first in the world 3D tablet running on Android. Another product that we have for high precision is this large camera. And what we're going to tell in a minute is how in this project funded by the PERTE chip, we're going to have the performance of this camera in this small form factor that will fit in a mobile phone or in a tablet. This is a comparison of how we do versus competition. At the left, you see a simultaneous red, green, and blue image. In this case, it's gray, and the depth map. This is the depth map. This is the RGB image. This is a competitor. That is the LiDAR at the top in the center in yellow and red, used in the Apple latest generations of mobile phones and tablets. You can see that they can hardly see the spokes of a bicycle wheel. And in red at the bottom is the depth map of the time of flight of the Huawei P30 Pro and the latest models of Huawei. The main competitive advantage is that we give 2 megapixels depth map, and the competition delivers a little bit more than BGA. So we are able to get the depth map of small objects competing for invisible for all the competing technologies. So the implications for augmented reality and mixed reality are huge. For example, does it work? Well, it doesn't seem to work. You see a flying object, a drone. These drones are used for countryside applications, and very often they hit into the wires, the electrical wires, to keep the cows and keep the horses inside a given area. With our technology, we can see from several meters distance, and when we approach, we see it even better, those small wires. And that's the reason why, for this kind of applications, we don't have any competition. But the implications for augmented reality and mixed reality are that we'll be able to handle much smaller objects, as I will show you in a minute. This is some industrial application of this particular camera. It is a high-end camera that can get up to 4 microns precision in the depth estimation. At the left is a beam peaking. You see the details of the depth map of the screws. We can look the length between two holes of the screw or between 2 peaks of the screw. At the right, you see an application for watch manufacturing. We have customers in the watch manufacturing area that they are able to guarantee in the final quality assurance that the needle of the seconds, it's 200 microns over the needle of the minutes, and this 200 microns over the needle of the hours, and so on for all the internal parts of the watch. There is another application in soldering. As you possibly know, the pin-through-hole soldering is not obsolete. It's needed, and even if some parts are able to pass the electrical tests, sometimes they fail because they don't have enough volume of soldering around the pin. Our technology measures the depth map of the solder and the volume of the soldering material around the pin. That if you don't have enough volume of soldering material, sooner or later will fail. And at the right of the image, let's check if this works now. Yes, at this right side of the image, you see the little volcanoes that we calculate the volume of those volcanoes to guarantee the reliability in the long term. This is an application of quality assurance for connector manufacturing. It's something impossible to do with a 2D camera or with a time of flight or with a LiDAR, and we can do it because we do both depth and image through a single lens. Let's check if this works. This, it will be invisible with a 2D camera, and it's impossible with some other competing technologies. Also, perhaps the most precise camera that we have is used to manufacture our own cameras. We put inside one of the Photonic machines our own camera to drive the robots. It's running much quicker and with much better precision. We have a customer in Eastern Europe that it's using our technology for collecting crops of strawberries. This is something that all the other technologies fail because the image matching between depth gets confused with lots of branches and lots of small details and several small fruits. It's a very promising application, even if it's not in volume production. This one at the right, it's automation in the manufacturing of cars, final quality assurance. We are able to guarantee with submicron precision that between the body of the car and the door of the car, there is a given distance, and we guarantee that the plane of the body and the plane of the door of the car, it's at the same depth, which is very difficult to do with the human eyes. Some of our customers are computing the volume of pills. These are pills from the pharmaceutical industry. You see at the left the image, and at the right the depth map. This is an application for medicine doctors. Basically, is this tablet with one of our cameras inside. And it's for doctors because traditionally, the way that they treat the patients with some diseases of the skin, basically they have some diseases that the skin gets sick for months or even for years. This way, they needed to put a ruler, take a photo. The problem is that if you take the ruler too near, you touch the wound. If you put the ruler too far, you are not measuring rightly. In our case, we have all the 3D model of wounds over the human skin. There are nearly 500 German doctors and a couple of doctors in Spain already testing these tablets, and our customer has put besides artificial intelligence to suggest the doctors the treatment for the particular wound. This is another application that we put together for some American doctors. They put a couple of lip retractors over the lips of a person, something like this. Then 3 cameras looking at the teeth from the front side, and 3 cameras looking at the face from the bottom, from the right, and from the left. We compute the 3D model of the teeth with 10 microns precision. Basically, our customers, some American doctors, what they do is they don't call themselves dentists. They call themselves smile designers. They take a 3D model of your teeth. They make a comparison of the 3D model seen from outside with our scanner with the intraoral scanner, and they decompose with some artificial intelligence software your smile the following day. You sign telling, yes, I agree if you do that. During the night, they manufacture the prosthesis. The following day, they inject the prosthesis within the teeth. They show you the photo. You fall in love with yourself due to your new teeth, and then you send a check of $20,000 for the dentist. The challenge of this application is 10 microns accuracy in the 3D model of the teeth, which, to my knowledge, we are the unique technology in the world able to do that. Let me check. This is another application that we use for measuring industrial pieces. However, I was surprised that all the major consumer electronic manufacturers of the world of smart glasses and people involved in augmented reality and mixed reality, they want to do this in Taiwan, in Japan, in United States. We thought that it was an application only for industrial applications, that is to have the 3D model of industrial pieces, but to our surprise, we have even customers in Korea that want to use this in restaurants, to do a 3D scanner of their dishes and to put it on the web to be more appealable to their customers. So let me play it again. Basically, this is a shoe being triggered with a 3D map and the image by our camera, and then you put together the 3D model of this little shoe. We did it mainly for some industrial applications, but it looks that all the major consumer companies of the world are interested in this, to my surprise. AR and VR. This is potentially our largest markets for several applications. You can see that this is a camera in the augmented reality glasses, virtual reality glasses, looking at your mouth. But it's a camera looking at your mouth from the front. So what the camera sees is the image at the top left, and our camera elaborates the depth map. And with that, we put together the 3D model. They want to use this, but it's not yet in volume production, for 3D video conferencing around the round table. So I have the virtual reality glasses. I look to my right, and I see the left side of the avatar sitting at my right in the virtual table. I look to my left, and I see the right side of the avatar sitting left to me in the virtual table. It's not going to be in production during the coming 3 months, but it's a very promising high-volume application. This is another high-volume application. Basically, in the augmented reality, mixed reality glasses, you put one of our cameras at the front, looking to your hands, and with your hands, you pick and you make bigger or smaller virtual objects. Virtual objects that they only exist floating in the air, and you only see them through your glasses. But the people don't see, only see that you are playing with air with your hands. Main competitive advantage here is that we can look and we can pick the smallest objects in the world. So we are able to interact with objects much smaller than competing technologies, time of flight, LiDAR, etc., etc. Let me trigger this. This is the video that we have shown to potential customers to convince them that we have a real-time correspondence between the image on the left and the depth map at the right. This is a virtual pistol, and you see two colors on the right that they are different depending on the depth and the distance from the hands to the camera. So hand tracking in augmented reality, mixed reality devices is going to be a big market. And I can tell you, not the names of our customers because we have NDAs, but everybody who is anybody in augmented reality, mixed reality, and virtual reality glasses has an evaluation kit from us. Some other potential applications that were not yet there, but they are high volume, is scanning objects with mobile phone to afterwards put them over a table, putting a virtual object over a real table, for augmented reality gaming, augmented reality applications. We have some customers that are exploring 3D secure payments. Is there anybody in the audience that knows the success rate of the iPhone latest model? How can you cheat the 3D recognition of the iPhone? Okay, Apple claims that only one person in 1 million can do the face recognition with your phone. Well, we didn't test so many, but 2 sisters that I know, that don't look alike at all, are able to cheat the Apple phone. With our face recognition based on the 3D volume of the face, we think that we are 100 times more precise than the iPhones. Let me go back, sorry. This application is also used by some of our customers for printing 3D objects. Basically, this is a strawberry through a single shot. We are able to reconstruct the 3D model with a single shot. If we had 2 or 3 cameras, or we have a sequence, for example, one of our next projects is to put one of our cameras in a mobile device and do a scanning of small objects. Just to scan this microphone, just we will need to move, and everything is running in real time in the processor of the mobile phone. And let's go to what we do and what we are going to do within this per-chip project. At the moment, the wafer level optics penetration, doesn't work this thing, is very low. We use traditional glass for the high-end cameras like this, and we use plastic molded lenses similar to mobile telephony in a small camera like that. But the wafer level optics, we use it only in the critical lenses that are 100 microns away from the silicon. So our future roadmap is going to be on wafer stacking. What you see here, the center, and this thing doesn't work either, but the center, it's some not glass stack, but a silicon polymer on glass stacked over each other. You see some wafers stacked over each other at the bottom right. And what you see as a roadmap for 2021, 24, 27 is not from me. Same as another speaker this morning, is from Joel Development, the market observers. We're going into that direction. We're going into digital optics too. At the bottom, you see 2 of the digital optics that we put together with one of the departments of this university. So what you see at the left is the roadmap according to your development, and what you see at the right at the center, it's our future roadmap. And we're going to do 2 things. We're going to evolve from analog optics to digital optics, and basically the blue thing that you see at the top right is the not X-ray, it's a cut of one of our cameras. And what we're going to do is to replace the plastic with digital optics. Digital optics is based in nanoimprint lithography. At the moment, the 2 companies of the world that are representing the state of the art, one of them in the United States and another one in Denmark, they have only 1 metal surface. In this project, it's for sure that we're going to go to 2, and we will try 4 and 6 metal surfaces and make them industrial and volume production shortly after the end of the project, because we are leaders in the design of new metal lenses with several surfaces. We are not yet leaders in the market because it's this American and this Danish company, but they chicken out when we want to work with them to tell we want 2, 4, 6 metal surfaces. And what you see at the bottom is that we are stacking the wafer of the CMOS image sensor with the wafer of the RISC-V processor. Some of the complaints of most of our customers is your technology is using 10% of the processor of the smart glasses to compute the depth map. That's not acceptable. We want 100% of the processor for gaming. That's why we had to put together a chip. And the best way to have a low-cost integration is through the stacked wafers of all the processor just at the bottom of the CMOS image sensor, without increasing the thickness of the whole device, because we do a back thinning of one of the two wafers. Well, this is going well beyond state-of-the-art in optical design. That's why we are working with University of Valencia. Very sorry that we're not working with you, but the physical optic guys at the other side of the city, they know more of optical design than we, the engineers. That's why we're working with them. And what is the RISC-V processor that is calculating the depth processing routines? We do it together with Semidynamics and the University of Murcia. Semidynamics is well known as a supplier of IP cores for RISC-V. And basically, partnership is the only way to reach steps well beyond the state of the art with people that know more than you. In this case, the University of Valencia knows about metasurface design, and the University of Murcia and Semidynamics are specialists in RISC-V processors and RISC-V modules. We have our own clean room, not for pleasure, for obligation. I'm not cheating if I tell you that I've been running around Taiwan, China, Japan, United States to look for a supplier. I even invented a new term called fabless silicon and optical vendor. We wanted to be a fabless silicon and optical vendor, but nobody in the whole earth could do the alignment between the optics and electronics with the 10 nanometers precision that we need for our cameras. So we have to put together, in collaboration with some other partners, our own machinery. The machinery, you put trays of components at one side, and you have tested cameras compliant to specifications to the other side. We are in discussion. We have a capacity of 100,000, as our engineers tells, 100,000 cameras per year, or 500,000 cameras per year, as the company that developed the machinery together with us tells. I still don't know, because we produce only tens of thousands. We didn't reach 100,000 yet, but we're going to expand the capacity of our clean room to potentially produce millions and hundreds of millions of cameras. A summary of our unique selling points. We are the unique technology in the world that is able to deliver 2D image and depth maps, that's 3D image, at the same time with a single camera without any need of pattern matching. We offer the highest resolution depth maps, 1.4 megapixels traditionally during the latest years, and 2.1 megapixels in a new model that we are launching next month. We have the lowest cost because the bill of materials is the simplest. We have the lowest power consumption because we don't need to broadcast infrared light to the world to expect that it comes back as time of flight. And this is extremely important in battery-operated devices as a smartphone and smart glasses. Lowest bulkiness. We have only one device instead of two devices. We have seen the time of flight presentation this morning. They need the vertical cavity surface emitting laser to emit, and they need a camera to receive the laser after bouncing the world. We have only one instead of two. And last but not least, we are extremely friendly with very sunny days at the open air. As you possibly know, all the technology is based on infrared being emitted to the world. They are not friends of sunny days. The more sunny that is the day, the best that our technology works. And last but not least, an observer like Joel Development, Joel Intelligence, is considering us, and you see our logo at the right side, as a potential substitute technology for what today are the leaders of the market, that is time of flight, structured light, and LiDAR. And that's basically it. Any question?
Thank you, Jorge. Do you have any questions?
Thank you. Very impressive talk. You talk about the precision of your depth measurement, and what about the range?
We are a short-range technology. We don't compete in the LiDAR for automotive applications going 200 meters ahead of the car. We are best below 1 meter. We can go up to 10 meters, even 50 meters, with very narrow field of view. But we're not going to those markets where LiDAR is best than us. We're going for applications like hand tracking, that it's below 1 meter, applications like lip tracking, where your camera is at 2, 3, 4, 5 centimeters from your lips. At 4, 5 centimeters, we are better, because to measure the speed of light over 2 centimeters is pretty difficult due to the phase error. We don't have phase error. We don't need image matching. The fact that in low distance there is a separation between the source of light and the camera for RGB and the camera for depth, it's something that we don't have. We have a single camera to look at both. So in short distances, especially microscopy or measurement of industrial devices, here I have a transparent watch. Afterwards you can look at it. We can measure all the layers and the separation between the different layers of machinery inside the watch. This is something that with a dual camera, time of flight and RGB, LiDAR and RGB, structured light and RGB, it's impossible because the two cameras cannot be together. Our cameras is a single camera, and both RGB and depth map go through the same optics. So in short distance, we will have no competition. Long distances, we are not going to those markets.
Congratulations for your amazing achievements. I have two questions. I don't know if you can give more details about the mechanism of how the camera works. I don't know. And say some words about that. And second question is, how much does it cost such a camera?
Well, I can give more details, but in order to explain properly, I will need another 2 hours. So, to simplify, the aberrations, optical aberrations that are produced at the image forming plane over the CMOS image sensor are proportional to distance. So, as good camera designers, we minimize aberrations and we maximize the modulation transfer function over a pattern of 3 by 3 pixels, but we maximize the aberrations over 1 pixel. So if we measure the light that should be in 1 pixel, that is around the 8 surrounding pixels, we measure in the center of the field the spheric aberration and the comma at the corners of the field. That's what we measure, and we compute distance based on that. That's a reply to the...
So it's not that lens moves, right? The lens is fixed.
No, the lens is fixed.
Okay. Thank you very much. Yeah.
And your second question was?
How much does it cost?
Yeah. This small camera, we can produce in volume by below $10. Well, if we get into it with one of the big guys, it will be well below $10 per unit. However, this camera, we sell it for $3,000, and we cannot produce enough. We cannot produce enough because 3D cameras for industrial applications, all of our competitors in that field sell them at $5,000, $10,000, and they use very sophisticated technologies that have a much more expensive bill of materials. The real reply to your question is the bill of materials. We have the lowest cost bill of materials because we have only one optics and only one CMOS image sensor. And the expensive thing that is now we need a personal computer or we need an XR2 from Qualcomm to make it run. We're taking it into our own chip that will produce the depth map and the image at 30, 60, 120 frames per second with minimal power consumption. So the only weak point that we have, we're going to tackle through this project.
Okay. Thank you.
Thanks.
Any other question?
I have a question regarding the meta services that you want to fabricate. Do you use standard lithography to produce those meta services?
Nanoimprint lithography, NIL.
Okay. Okay, thank you.
And I have a question regarding the meta surfaces as well. So you mentioned that the alignment tolerances are very tight in your process, right? In the order of 10 nanometers, you mentioned?
That's correct.
That's extreme, right? Does this impact the resolution that you will need on the alignment of the meta surface later on?
Well, a meta surface it's optically equivalent to the lenses that we have nowadays. So the alignment is something that we have fixed with the current lenses based on plastic in this case and based on glass in this case. But the meta lenses, the only thing that they will do is reduce the size of this camera to this size. But optically, basically we will put a camera like this, much better than any camera in any mobile phone, within a small form factor. That's what the meta lenses will do. The alignment problem is fixed already.
Yeah, so you will not be able to relax the alignment tolerances by using the meta surface?
Never.
Yeah, okay. Very impressive. Okay, so let's thank Jorge once again, please.
Thank you.
And now, just before lunch, we are a bit ahead of time. Sergio Saez from SECFO will have some words for all of us.
Gracias.
Thank you. Thank you. Well, first of all, let's close this second block of the day. But first of all, please let me tell you sorry, because this morning I felt a puncture in my lung and I had to stop. But I'm still alive. Then I will go to the doctor this week because I'm pretty young, I think. And well, let me introduce you the B2B meetings. I don't know if you can put the presentation. Okay, let me introduce these B2B meetings. Now we will go to the lunch and we will come back at 3:30. We will have, at 3 o'clock? Okay, at 3, sorry. We will have the next block of presentations, and at 5, we will have the B2B meetings. We have prepared from SECFO, and you will see here that there are 4 slots at 5, 5:30, 6, and 6:30. We will have 9 or more meeting corners. In these 2 corridors, we will put the different meeting corners. You can see if you are here in one of these slots. In case you are not, because you didn't have a meeting, but now you decided that maybe it's a good idea to have a meeting with any one of the other participants, please tell me. At 5 o'clock and during these 2 hours, I will be outside in the corridor in that meeting point. You can come and I will put you in contact with some of the other participants in order to have a meeting. We don't only have these 9 meeting corners because this auditorium is very big, and I will put different numbers around. And that's it. Please be aware if your name is there. And in case you want to change something, please tell me, because I can arrange the meeting in another time or another place, okay? Then, but before the lunch, then the next block of presentations at 3, and this will be at 5, okay? Thank you.
De hecho, mira. Adaptadores, pero. Yo lo tengo, pero en mi despacho. A ver qué tiene. No, que yo lo tengo, pero en mi despacho. ¿Puedo mandar un email aquí? ¿Hay alguna cuenta o no? Tú mándame el email y yo.
Hello, everybody. Yeah, that's better. Welcome to this third session of the Photonic Integration Week. We'll start off with a talk of Salvador Coy. Salvador, welcome, and the floor is yours.
Thank you very much. Muchas gracias. Thank you. Good afternoon to everyone. Well, thank you for the invitation, and thanks to the organizers, to UPV Fab and all the team for challenging me in giving a talk here to you, not for a technical perspective, but more on the type of activities we promote at the university to try to make things happen in photonics. In particular, I will talk about our ecosystem to promote the creation of spin-offs and startups. In my role as a vice rector for innovation and transfer, we try to connect the main university asset, which is the knowledge, with the needs that we detect in the society. And we try to generate tools, generate channels, interconnections, and help things happen in this interaction at any level, not only in the traditional way tech transfer uses to happen, from the research results, the patents and the patent licensing or spin-off creation, but also taking into account that part of the impact we generate in the society comes with our graduates, our PhDs, tailor-made courses for companies, company chairs, internships by our students, companies being created and promoted by students, not only by professors or researchers on top of research results, groups of students that try to solve global challenges in a competitive way and organize themselves independently from the university, let's say, management, and so on and so forth. And we try to coordinate all these activities because all of them share the same space, connecting knowledge with impact. In particular, I would like to highlight what we do in terms of promoting the development of spin-off companies at UPV. And in particular, although we don't work in a, let's say, specialized way, or we don't have specific tools for one particular field of knowledge, I will dedicate the end of the talk to present very briefly several of the initiatives we started on photonics or related to photonics, although some of them will participate in these sessions, one afterwards and another one tomorrow. The actions we organize by the university are set up by the Knowledge Transfer Office of the UPV, which is called UPV Innovation. Although the name is Knowledge Transfer Office, is not a centralized service, but a constellation of different services that work together in coordination. Because as I mentioned at the beginning, we have many tools that connect knowledge with impact. And all of those tools share the same space, share the vision to generate impact in the society, and the difference is the solution we provide to the society. Sometimes it's a graduate, sometimes it's a doctorate, sometimes it's a research project in cooperation, sometimes it's a startup company providing solutions, sometimes it's a spin-off company being invested by an external company, sometimes it's an internship, sometimes it's a company chair, etc., etc. And we share these two mottos, okay? The vision, in which we try to promote through our strategic plan, which is named Sirve in Spanish, which means serve in English, because we have the the understanding that the university has to provide services to society. We are a public university and we are devoted to generate impact. And SIRVE, in the Spanish naming, stands from sustainable, international, relevant, vital, thinking of persons, people, and excellent. That's the naming of the SIRVE word for our strategic plan. And in this plan, we try to increase the way, the intensity in which we generate impact in our environment, providing these four main aspects of these four main pillars: talent, persons, people, training, customized training products, not only regular degrees or regular master programs, knowledge in terms of capabilities of our researchers in providing solutions to challenges, and entrepreneurship, both providing solutions as providers of solutions and also being recipients, receiving investment. Okay? And the vision that makes us think in this way is that we think that we have to be, as a university, among the top 5 entities at the regional level contributing to the socio-economic development of the Comunitat Valenciana, which is our region, and also with an impact at an international level. In this framework, why promote a spin-off companies? Well, we are very well aligned with these principles I mentioned at the beginning. We want to contribute to the renewal of the economic fabric. If the future depends on being more knowledge intensive in our economic activity, the university that is generating new knowledge has to play a principal role in this scenario. Of course, we would like to generate value with our research results. Sometimes corporations are looking for technology not in terms of patents or research results, but in terms of business models that have been already tested. Then we have to somehow make our results to evolve, to mature, and to create small businesses that prove that the business model is reasonable and this investment opportunity is there. And many times, big corporations that come here are not looking for patents, they are looking for business models built up on top of patents, and somebody else has already validated that in the first place, which is where we have more risk. Of course, creating new economy is a good opportunity for our PhDs and graduates. We are having a reasonable success with our current spin-off companies. We started with the first spin-off in 2005, I think, or 6. And we started a couple of years ago, or 3 years ago, with a pilot experience with one of our research institutes, the one that is hosting in part activity in photonics. And we, after testing the methodology and the processes during that pilot experience, we extended the SPIN UPV program to all the university, which is this SPIN UPV project is the one that is promoting the creation of spin-off companies at university level. Well, this SPIN UPV is not an isolated action. It's included in the second pillar of these 4 sections we can see on the slide, because we as a knowledge transfer office, UPV innovation, we work in 4 dimensions: engaging, we try to cultivate relationships with external partners, typically companies, industry, sometimes non-profit organizations, the public administration, cultivate the relationships, not only make a contract, but on a continuous way, keep that relationship alive, okay? That's the first pillar. The second one is what we can understand as the traditional tech transfer actions, IPR valorization, that starts from the protection of the research results and its their valorization through licensing or through spin-off creation. The third pillar is promoting the innovation culture in the university community. We would like to make our professors, students, administrative staff to live in this culture where they are part of a strategy that tries to promote the development of our region. And participation. We try to make the people involved in this project to be engaged and participate in the actions, because we are a lot of people. At the bottom of the slide, you have the different names of the different units, services, entities that participate in these actions at different levels. There are many different services with different directors, different objectives every year, and we try to coordinate them all under this umbrella of the Knowledge Transfer Office and organize all the activities and coordinate all the efforts in these 4 pillars. Spin UPV, which is the action that promotes the creation of new spin-off companies, is located in the 2nd pillar. And as I mentioned, this is not an isolated action. It's in red on that box over there on the right-hand side corner of the slide. But we have these 4 dimensions: engaging, valorization, culture, and participation. Each one of them contains different, let's say, black boxes that are different services that or different actions or projects that we are developing in each one of the pillars. And every group of actions in every pillar has a management team that is responsible to accompany these different actions and make things happen and coordinating all the activities. And we have also, in the participation pillar, the last one, all these team coordinators participate. There's an innovation committee at director's level, where it's different vice rectors of the university, innovation and transfer, myself, entrepreneurship, research, culture, communication, all of them together, taking care of the objectives we fix every year and trying to analyze the impact of what we do. And of course, we have a UPV Innovation Plenary where everyone is called, which is right now composed of around 90 people that partially are involved in all these activities that are coordinated under this umbrella. What about the actions we do in the promotion of new spin-off companies? Well, we understand the startup creation as a validation process. And we have to validate the product. And in this process, sometimes we have to increase the TRL. We have to validate the market. We have to validate the team, the people, the persons involved in the project. And we have to validate the financial aspects of the project. And in our terminology at UPV level, we use the naming startup and a spin-off with different meanings, with slightly different meanings. Although they are synonyms, we use the term startup for companies being promoted by students, normally not having patents owned by the university, and spin-offs when the technology is owned by the university and the team is composed of professors or researchers that were involved in the production of the results that produce the patent. Okay, and the methodology has switched from being reactive to proactive. In the beginning of this type of services, the Tech Transfer Office waited the projects to knock on the door, and some professors and researchers told us that I would like to start a new company. And then we help in the process at business level and tech transfer level, and we try to connect the projects with investors and so on and so forth. Right now, we don't work in that way. What we do is that we identify every year in December, we identify the technologies being developed during the past year, all the new patents. We patent around 40 new technologies and 25, we register 25 or 30 software pieces every year. We analyze all these pieces of technology. We try to detect which ones we think they are promising or they can be a seed for a new company. And we actively make the authors get involved in the spin UPV project. That will last during 1 year. Once we detect those projects, we start the process that will combine different ingredients. Training, team building, team completion, trying to include business talent, business experience that typically is not provided by the research team itself, and investment at the end of the year. And during 1 year, we work on a very well-defined procedure to speed up the process of creation of new companies. This is the training program. We are right now, today, there was a training pill. They're very short. They're devoted to researchers and professors. Everyone is very busy. 2 hours long introductions with invited talks by external professionals in different aspects involved in the creation of new companies. After that, we have the team building. For every team, we organize around every one of the technologies. We make a networking session to connect team project teams, with what we call, it's not included here, we call them pro-CEOs. They are not the CEOs of the companies, but they are business professionals that have senior experience and can get involved in new companies at risk, because we can't pay the salaries of those profiles. If there is a match in between the technical people and the business people, then the team forms, and that is compulsory for having the support of the program. And then that team is the one that will develop the business project during the year. We have financial aid also. We have some, as much as we can, some amount of money to dedicate that to speed up the processes, the projects. Part of the money is for business development, which is what we call the line 1, and the line 2 is for technical development, because many times the technology requires some scaling out of the laboratory to increase the TRL level of the technology, and we can provide some resources for every one of the projects. And for this financial aid, we have the evaluation window is open all year long, and we have 3 deadlines where we look at the applications we received, and we distribute, for the good ones, we distribute the different financial grants in order to make things follow the readiness of each one of the projects. The line 2, which is the one which is evaluated, which is provides 40,000 euro per project, is one that is evaluated with external professionals. It's not an internal evaluation, and we evaluate this for different aspects of each one of the projects. And in the kickoff that we realized we celebrated on this 22nd of February, we organized that first meeting in between members of the team, different teams, and the possible CEOs that can be working together in each one of the projects. The team presents one slide per person, the CEO presents one slide, and then we organize the interactions in between them, trying to make very powerful teams, providing this business experience that typically was not present in our original projects when we started. Well, this is the team, the people behind the project, managing the different actions. We have the web page where everything is promoted at the university level, but we have this proactive activity trying to make professors and researchers get involved in this type of projects. And a few examples, summarizing some of the examples that made us think that we could move further and switch from this reactive way of doing things to a proactive, and trying to create not 1 or 2 spin-offs per year, but 5 to 10. Some of the success stories are companies around the photonic field. The first one, I ordered them in chronological order, and some of them we participate in the seminar, in these sessions today and tomorrow, and we will have the opportunity to know more about them. The first one was DAS Photonics, DAS from Defense and Aerospace. That was our first, in fact, that was our first spin-off company back in 2005. On that date, we even didn't have regulations internally to define how to make things. Now we do. VLC Photonics is the second one in the history. Inigo will participate in half an hour after me. I think he will talk about VLC Photonics. This is a glimpse of the web page of the company that was started in 2011. Is now in a very significant increase in activity, 25 people located here, both the technical part and the offices are located in our premises, in this building and another building nearby, and is part of the Hitachi Tech Group since 2020. This is one of our success stories that make us think we can go even further. CalSense is a company using also light as one of the key principles of its technology, but in this case, they use the fiber optic sensors to monitor originally infrastructures. Okay, they can use this or their knowledge to measure extreme temperatures, shape. You look at that picture over there at the bottom on the right, where the diagram on the graph, on the plot, is exactly the same shape in which you bend the optic fiber. They can exactly detect all that from one end of the fiber and measure gas presence, pressure, etc. Main applications in monitoring infrastructures, civil engineering infrastructures. This is more or less its history. Hyperonics, the youngest one in this field of photonics. Daniel will speak tomorrow in the morning. You will have the opportunity to interact with him. They are leveraging the design of programmable photonic devices. Very talented set of group of people, and with a very promising future ahead. And well, that's it. That's a summary of what we do in terms of promoting the impact generated in the economy from technology, and in particular from photonics. Thank you very much for your attention.
Thank you very much, Salvador. Are there any questions for Salvador?
Yeah, thanks, Salva, for the nice talk. I have so the question is the first year you're starting this initiative or of scouting on the technology and trying to set up companies?
No, it's not. In fact, it's not the first year. It's not the first year. We started with a pilot project back in 2020, I think, with iTeam, with the iTeam Research Institute, focusing on one research institute, in particular the one promoting many of the photonic spin-offs, trying to test the methodology with one research institute that was productive enough to test more than one example per year. And in that pilot experience, I think we didn't create any company, but we tested the methodology, and I think that many of the actions we did that year helped on the years after.
No, but the question is, are the professors or the knowledge generators reluctant to enter into this business?
Well, if
or do you have to force them to go?
Well, we have to press a little bit, but we think that we have the responsibility of doing that, and our thinking is that if there is an opportunity for a technology developed here that, according to our legislation, is owned by the university, if there is an opportunity to make this technology generate economic results in our region, that would be perfect. But for the world also, if there is an opportunity, we have to try that as much as we can. And if the professor doesn't want, let's try it, although he doesn't. Of course, we need some level of involvement. Otherwise, he or she or they are the authors of the technology. They have to be involved in the process of the creation of the company, at least at the beginning. But we are trying to put all the pieces that can be replaceable. The technology is not replaceable, and the author is not replaceable. We need some level of involvement. But let's try to put the business people, the money as much as we can, the space if we can, try to connect with investors, make things as, let's say, easy as we could. That's the point. And if they are reluctant or not, we think that we have not exhausted the capability of our community, because every year we are identifying in between 15 and 25 new teams, new projects. Then we will keep going and see what happens. Okay. The point is, let's try to create all the companies that should be created, and not, otherwise it's a pity, producing results and placing them in a drawer and wait someone comes and seek for them. We have this responsibility of put as much energy as we can. That's the point.
Any other question? Okay, thank you, Salvador.
Okay, thank you very much. Enjoy your stay in Valencia. Thank you.
¿Sabes cómo abrirlo? ¿Cómo pueden? Porque es en español, no sé.
No sé si es aquí. ¿Control L? Ponte.
No, esto no. ¿No va? Convertir, no es el. Emisor. Ahí, se ha dejado.
Vale.
Okay, then it's time for the second talk. We welcome Carlos Abayan from QSite. Carlos, the floor is yours.
Thank you very much. Good afternoon, everybody. So Pascual actually asked me this time to explain something slightly different. So in earlier editions, I talked about QSite and the technology, but this time he asked me to explain a bit more about the journey of our company. We are also a spin-off company, so it was interesting to see what UPV is doing. There are some similarities in our journey. Some things will be different. So in the next 25, 30 minutes, I will be talking about our journey. That does not mean this is the prototype journey or the way to do it. It's our way in which it turned out to be. So maybe there are some lessons learned, some things that you may use, some things that you may use for not how to do it. Good. I'll tell you a bit about QSite for those of you that do not know who we are. And then I'll talk to you about how did we move from research into a spin-off, then from the moment of spinning off to closing a Series A round, and then from that Series A round to today. More or less, in research, we were about 5 years of development. Then the first seed funding round were like about 3 years, and then about 2 or 3 years since we closed Series A. So at QSite, we are a company, we are a spin-off from ICFO, and we specialized in what we call randomness solutions, right? Which is something a bit very specific, but then we apply it to 2 markets. Market number 1 is cryptography, where basically the application is to make secure communications and enhance the security of systems. And in efficient computation, where here is what we call a stochastic acceleration. This is about compute efficiency and compute performance, right? So these are 2 different markets, everything around randomness. That's the core of what we do in the company. Cryptography, we call it entropy generation, because entropy is this resource that we need in cryptography. No entropy, no security. And in cryptography, we call it, again, stochastic acceleration, and I will tell you a bit more about that. So what is the entropy problem? Why are we even working on this? So random numbers turns out to be at the foundation of most of the software that we use every day, right? And that's a bit surprising, but every time we connect to our bank online or we send a WhatsApp message, whatever, we use random numbers. Random numbers is actually this resource that allows secure communications to operate. If you're in cryptography, there is this Kirchhoff principle that says that everything in a cryptographic system is public, is known, is open, it goes through peer review process. There is just one thing you need to make sure you keep safe, which are the random numbers, the cryptographic keys that you use. Then the question is, are the random numbers we use good enough or not? Okay, that was a question that actually started most of this research and that still drives most of the commercial activity. A lot of people say, yeah, this is problem solved, but we keep seeing innovation year on year, new products being certified and standardized, and new failures in the marketplace. One of the latest one in March 2023 was by Syscoin, one of their firewall products. There was a problem because the entropy, so basically the vulnerability report, because in cryptography you need to report the issues you have. Cisco routers, blah, blah. There was a security vulnerability due to low entropy keys. Low entropy keys means your random numbers were not good enough, or you did not have enough. Okay? So this keeps happening. Samsung also had issues, and many other elements. So potentially the question, are they good enough, is no, and then there is room for better technologies. At QSite, we've been developing randomness solutions for more than 10 years. We today have, we can produce wafer scale, we have wafer scale capabilities for quantum entropy sources. What you see on the slide is an indium phosphide wafer that contains quantum entropy sources, which is based on a process we call phase diffusion, and I'll give you a little bit more details about that. We have 2 random number generation platforms, one in indium phosphide, the other in gallium arsenide, with 2 different performance ranges. And we are working with global customers and channels. A team of about 45 people, and very intensive on patents. We have about 20 patent families. That turns out to be a portfolio of more than 50 as we speak. The Series A that was closed in 2022, and 2 product families, one for cryptography and one for compute. The products for cryptography are the 2 first that you see on the slide. Entropy chips are basically this component. It's a photonic technology. We call it photonic inside, electronic outside. The reason is that all of the photonics are inside of our chip. Basically, we have lasers and detectors, so we have to drive RF and read RF. That means it's very convenient at the packaging level and at the system integration level. So quite easy. And then those are actually commercially available. Then we sell the quantum random number generation technologies on different form factors. The one that you see on the slide is, we call it FMC. And this is for, basically the customers here are system makers with FPGAs. This is a standard interface, so it's a plug and play device. We also have PCI Express. We used to have a full length PCI Express. We just announced last week low profile, which is we reduce the size, the area by 2. And PCI Express available at 1 gigabit per second and 100 megabit per second. That's the other thing we launched. And then the other product family is, we call it RPU, from randomness processing units, basically, and I'll tell you more how this product line came, because this actually, we created this product after working with customers. This was not something that we originally wanted to do, so by working with customers and understanding what value we were driving them, we actually came up with this new product line. So from research to spin-off, and I'll need to control the timing because this presentation is not a typical thing I give. What did happen? So the project started, look at the first results. This is a paper of 2011, right? So colleagues of mine at ICFO, back in 2011, they published a first paper that by gain switching a laser, that means driving a laser from below to above threshold and doing it in a proper way, you can exploit fluctuations in the laser cavity to generate random numbers. So first paper was in 2011. The second paper, that was basically a deep down physical analysis that we collaborated here with people from BLC, Japanese group, Pascual, to understand the physics and to push the performance as much as possible. It's 2014. That project, when I joined, was 2012. So for quite a while, it was really, really elementary at the tabletop environment, even if it's a very simple physical system, right? So you have the laser, you have an unbalanced Mach-Zehnder interferometer, so you delay 1 pulse to the previous one, and you interfere 2 pulses, each one with a random phase, and you translate random phase to random amplitude that you can photodetect and digitize. That was the research part. An aspect that is not that known, because we never published that except on my bachelor thesis, is that prototype. So that was the first time we built a device, a system. We actually took that, put it on a luggage, carried it to Japan, got into a train in Japan, into a research center on top of a hill, nuclear fusion science simulations. That was the first time someone used the random numbers in a Monte Carlo simulation. Actually, the device didn't work when we left Barcelona after an overnight trying to make it work, but we made it work real time in there. So that was a device that was implementing this high rate randomness applied to cryptography. So very early on, we already had that spirit of taking the science, building devices, and someone else to use those devices. So that was probably the first set of results, understanding this phase diffusion process, experimenting, publishing, and building prototypes. Then the second part of the journey, and that's quite a remarkable one, and also something that is fundamental today in our value proposition, was, okay, we're building those devices, but how do we know that what we're producing is random? How do we know that that comes from that quantum mechanical process or that photonic process or not? So we invented, actually with one of my supervisors, that he's on quantum optics experiments and metrology, he said, look, we can measure really very precise stuff on atomic clocks. We can do metrology. We know how to do that. Why don't we apply those techniques to measure randomness? And that turned out to be possible, right? So we developed this methodology. We call it randomness metrology. And basically, to get an intuition on what that means, when people think about randomness testing, what you think is, okay, give me a sequence of random bits, and then I will test if that's random or not, right? I will apply this battery of tests, and if there is biases or correlations, you name it. But that's fundamentally incorrect for cryptographic purposes. Why? Because if I give you a sequence, and let's assume it comes from a perfect device, you will pass the tests. Maybe sometimes you fail them, and that's a good thing. But let's say you pass the test. Now I give that sequence to your adversary, and that adversary will take the sequence and will pass the test. It looks random as well. And then that means that that sequence can be reused many, many times. So to test unpredictability, this method is not good enough. So what is good enough? Because this unpredictability can only be produced in hardware, you need to go and test and do metrology on the hardware. And that's what we proposed. So we combined the performance and the speed from the first experiments with the ability to measure the quality, and then we built a series of devices that you see on that screen. That's probably the return on the investment on that year building devices was very high. We ended up publishing 3 PRL papers, 2 Nature papers came out after that as well, because they were used in the loophole-free bell tests. So those devices at the end were used in the experiments that 2022 got the Nobel Prize in Physics. And the reason was the performance and the ability to measure the quality of the randomness in a rigorous way. So that actually changed a bit our field. Today there are other people in research that are using these techniques to measure quality of the randomness. So today doing statistical tests is no longer good enough. Okay? So that was the second stage. And the third stage was, okay, we can build devices, the science is done, we can measure the quality, but these big boxes will never make it at the practical level. So we started doing stuff with photonic integrated circuits. On the left, you see the first indium phosphide quantum entropy source chip. We did that at HHI. We again collaborated with people here in Valencia from BLC, from UPV, and it worked. Let's say we built around 4 chips, 2 didn't work, 1 broke. The 4th one, we managed to publish a paper. And that was actually the seed of what then went to become QSight. But at that time, we didn't know if we were going indium phosphide. There was also silicon photonics, so we built a silicon photonics chip. The problem, as you know, we did not have a laser on that silicon photonic chip, but we had the unbalanced Mach-Zehnder interferometer, the photodetectors. The laser was external. We also tested it. It was relatively successful, but as a company, we decided to go indium phosphide because we can do monolithic manufacturing of the devices. We don't need external coupling, external processes, and that was the choice that we made. So that was the scientific aspect. That's where we were before we spun out. Okay? So the science was done, validated, published. We invented the metrology, and we did photonic chips we could scale. And the next aspect was spinning off. And I'm highlighting three aspects. One was the enrollment of KTT, the Knowledge and Technology Transfer Unit at ICFO, not at QSight, at ICFO. A team led by Silvia Carrasco, she's on the picture, also Sergi Ferrando was working on that team. From the very beginning of the journey, when I joined in 2012, they were involved, right? So what they were saying a few minutes ago, that the university scouts and then leads the effort, that's something that probably is not exactly the same, but at ICFO happens. From the very beginning, KTT team gets involved and works with the team to keep the mindset where potentially there can be exploitation. And they were with us like 4 or 5 years until we spun out. The second aspect is during that time, we were not only doing the science. And KTT was facilitating that. ICFO was giving us that opportunity. We also wanted to do it, right? But we did business training. In this case, it was a program with Berkeley, with the Haas School of Business. They invented all of this lean startup methodology. So we were for an entire 3 or 4 months doing that training. We even went to California. That was a very good exercise. That was during the research time, and we did others with business schools in Barcelona. Then we did all of that. We decided we needed a team, and we needed investment. So that's a composition of the founding team. My 2 supervisors, Valerio and Morgan, co-founders of the company. And then the 3 guys that we went full-time into the company, Waldimar Amaya, former well-known here in this school. He joined us. He's leading all of the engineering and production at QSight. I went to become also the CEO. And then Domenico, he was not in our project. He was actually a former PhD student. But for us and our business model, scaling and getting the photonic chips in place was fundamental. This was really core to what we wanted to do as a company. So actually, we brought him back into QSight to lead all the technology development. And then with this configuration, the science, we actually secured seed investment from a US-based business angel. And the focus was really on validating the technology. There was some business, but at the end for us, the vision was clear. Entropy is needed in cryptography. The question is, we did 4 chips at HHI, 2 didn't work, 1 broke, we got 1 left. So can we produce this and actually build a product? Was the question mark. We needed to figure out if that was possible. So that was the main focus of our seed round. Can we even produce those chips? So from spin-off to Series A, I will need to speed up a bit. three main categories. So during these first 2-3 years, we validated that technology milestone. So we managed to be able to manufacture full wafers that worked, that we could implement the phase diffusion quantum random number generation technology. That was not a beautiful process that worked every single step of the road. The first wafers we didn't work, right? So an entire set of wafers had an issue, and then we had to figure that out. We were working with people here that help us actually get that up and running back again. So we managed to validate the entire process. So we could manufacture full wafers of chips. Then we could also very cost effectively package them. You can see on the screen two QFN packages, if I don't recall incorrectly. One was 8x8, the first one we did, but we had plenty of space. The die is 2x1 in our case. Then we did a 5x5, and we streamlined that. The core package at QSite today is a 5x5 QFN package for this QN100 chip. And on top of that, because at the end we were a company, those chips were a development effort, definitely not at the place that we could sell them. We actually put together what we would call the first product of QSite, so we can call it an MVP, whatever, something that allowed us to ship to customers. We call this the FMC 400. We also had the PCI Express, and this was done with off-the-shelf components. We had bulk lasers with fiber optics rolled into that package, but we could build and ship those things to early customers. That was also a very good step and validation for us. The second thing that happened was that the early commercial traction, and we onboarded the sales team. There are examples here from Telefonica, from CaixaBank, from Juniper, work that we did, and other customers. So because of the field we are in, sometimes we cannot disclose some of the work we do, but these were some good examples that were published, and we onboarded sales team, right? So again, the goal was, can we produce the wafers? Yes. Eventually, we needed to build the sales rigor in place, so we attracted a very senior sales executive that started to put that in place. So we moved to from having a few customer conversations a week to having the agenda fully booked week on week on customer conversations. So that was a very good step. And the third one was we started to close contract. And the first one was in the space industry. And we continue to work in the space industry to put the QRNG technology in space, mostly in Europe, European Space Agency driven, but also in research. So we got this was a contract with ETH, very specific, but it allowed us to develop, build technology, put it out, and get the team on the mood from we are not a research entity, we're doing products and we're serving customers. And then that process ended up with our Series A round that was led by Trumpf Ventures, the venture arm from the German group, Trumpf, and Bullnet Capital here in the room, and we have several of the other invested companies from Bullnet in this room. So where were we at that time, right? We validated the chip technology, we could produce it at scale, we could launch and ship products and attract technology talent, so we had everything ready at the technology level, and we demonstrated early customer traction and shippings and ability to secure sales team. So the idea for the Series A was clear. First was, we have products, we can ship them, we can build a business and grow it. So that was one aspect of the Series A focus. The second area of the focus was to scale the technology. Again, we can produce those chips at wafer scale, and that's great, and that's scalable per se. But if you think from the customer perspective, that is not enough. Because this is a photonic chip, let's not forget about that. You need electronics to make those lasers switch on. And if you can make a very scalable photonic chip, but what you need to make it work is a nightmare, it will not scale as we have. So continuing to push on high volume capabilities so that the total cost of ownership, if you want, for the customer is easy, was the second aspect. So this was what led to closing the Series A round. So from Series A to today, where are we? One of the things that changed majorly has nothing to do with QSite, and is the fact that today the world is transitioning to quantum-safe cryptography, right? So irrespective of us being here or not, there are new standards on post-quantum cryptography. Europe is investing in quantum cryptography, so this is happening and customers are starting to migrate. Enterprises need actually a plan to migrate to quantum-safe cryptography. This picture is actually from an event that we organized in Barcelona with customers and partners. It was a very great event last year. We will do it again this year. Here are a bunch of customers or partners that we're working with. That is happening today, and we can feel it, right? So we see that customers are starting to deploy these sort of technologies. The second is that once we have the technology, right? So it's not a mystery anymore how we can produce these chips and put them into products and make them work. So we know how to do that. Now we're more targeted and focused on what products we launch for what segments. The RPU was an example. We were working with CaixaBank. Our mental bias from research was we build better random numbers so we get better security systems. And we applied the same logic naturally to other markets. We make better random numbers, we get better simulation results. And that's true, and in some cases it's the case, but it is a very hard sell. But what we realized working with in this case was CaixaBank, was that the entire simulation that they were running was running 10 times faster and with 20 times less energy consumption than if they were doing it on the rack with a server. So it was not that much about the quality of the randomness. That was a good to have thing. It was really about the performance and the energy efficiency that they could get. So we changed the product and we started to commercialize this randomness processing unit. We also made it available in the Amazon Web Services marketplace, so you can go there and spin it, but you need to ask us first, so it's not open on the public. I'll skip this use case because we'll not have time. Second one, we launched the 1 gigabit per second QRNG. Now we got the chip. It was ready, so we could bring it into our product. So remember the big box on the FMC 400? We don't need that box anymore. We have a fully integrated version, that's the FMC. We also have the PCI Express form factor. Then the PCIe, we made it smaller, actually from customer request. They said, the product is good, the performance is what we need, but our server is smaller than you expected, so you need to make the product smaller. So we made it smaller, and we launched what we call the low-profile PCI Express. This is ready, this is a single board, and it's really a beautiful, industrially scalable PCI Express product based on the photonic chips that we manufacture. And the latest that we're putting together is this Entropy Core that combines this form factor that is an appliance, and not only the appliance and the technology inside, but also the connections. We have deployed this into one of the largest data centers in the world. It will be public probably in 1 month or two, and we're very, very excited about this one. It will actually reduce the barriers for adopting this technology in secure infrastructure massively. So we expect this to open up new avenues for us to bring the technology to enterprise market. And then on the scaling side, I talked to you about the market. Remember the two objectives: consolidate access to the markets with the products you have, and second, continue to scale. We now have full wafer scale processing and packaging from the QN100 chips. You see a wafer that's cut. We can now take that wafer, ship it to the packager directly, and then they package it. So it's not only the manufacturing, it's now the entire value chain that is streamlined. And the second stuff that we did, the QN chip is a very unique product because it gives you on a 2x1 millimeter square gigabits per second. No one else can do this performance level today, and definitely not at the scale that we do. But if you don't need a gigabit per second, that's a bit too much, right? In that case, we actually started investing in another technology back in 2017 that at the expense of not having the speed, still it can work 5 to 10 times faster than competing technologies. But working at 50 megabit per second, we can make a very scalable technology. This is based on pixel devices, exploits polarization switching dynamics, and that's part of the reason some of the investors that joined in our Series A actually also joined at that time. So what's next for us? So we're in the 7th, maybe next year I can explain it. But as a bottom line for QSight, we have had these 3 stages from research to spin-off, where basically the pioneering work, the science was important. Our seed stage was really technological, building the capabilities and demonstrating this photonic technology can scale in volumes and cost, and building the commercial rigor. And then the Series A for us has been purely the commercial focus has been the major thing that we've been concentrating with and that we continue to be focused on. That help us be more focused, that help us launch products that are better targeted to what customer needs. And that's basically where we are today. So hopefully maybe next year, if Pascual is still willing to extend an invitation, we'll be more than happy to come and tell you more about it. So hope this was useful for some of you if you're thinking to spinning off or early stage in the process. And if not, I hope you enjoyed a bit the presentation. Thank you very much. And by the way, unfortunately, I will need to jump quickly to grab a train. If anyone wants to talk, feel free to drop me a note. It's carlos@qsight.com.
Okay, thank you, Carlos. Thank you for the very interesting talk. Are there any questions?
First of all, congratulations for the outstanding achievements, Congratulations to you and the whole team. I just want to ask a question. Feel free not to reply if it's confidential. What was your revenue, your sales figure last year?
I can tell you what we expect this year.
Yes.
We expect to cross €2 million this year.
Congratulations again.
Thank you.
Okay, any other question? Good, then I have one question. Like, I understand your random number generation is truly random and in that sense better than the conventional way. But does that also mean that encryption using conventional random number generation is then flawed, or can it be good enough?
So so if you go to a customer today, right, the reality is people are using technologies that are non-quantum based for entropy generation, right? Yep. And this is what the market is using today. Now, one of the biggest challenges is, and then we continue to see flaws on that perspective, people cannot know if what they're producing is good enough, right? So somehow you just rely it is, but you cannot have any certainty, right? So this technology allows you to do two things. We call it on this enough. Is it enough? There are two metrics. One, is it enough in terms of volume, in terms of performance? Do you get enough random numbers? So the performance is a very important angle. And today, the performance is low. What you can get from classical hardware and typically in servers is poor. So you get enough in terms of volume. And in terms of quality, the problem is that today you simply cannot know if it's enough in terms of quality, and now you have visibility. So is it a disaster? No. Can you do better? Yes. And then companies, there are two profiles. The ones that are more innovative and they say, yeah, I want to do better, and then I'm investing in these new technologies, and then people that will be following more later on, right? So what I'm doing is good enough, and then when my customers ask for it, I will put it in. So we have a bit of the both.
Okay, thank you. Okay, let's thank Carlos again.
Thank you.
Okay, and then let's welcome Inigo Artundo from VLC Photonics. Inigo, the floor is yours.
Thanks a lot. So, yeah, I'm Inigo Artundo from VLC Photonics. I guess most of you already know me. But I'll be introducing a topic that I think we have been hearing already in this session for quite some presentations, which is what are the challenges? What are the challenges to take an idea from R&D as a spin-off company maybe to full-scale production as a grown-up company? So first of all, a little introduction about VLC. You have seen already this in the presentation by Salvador Sales. So we actually spin off from this same university, from the group of telecommunications and the R&D research group on photonic integration back in 2011. So we are more than 12 years old. We still have our offices and laboratories and clean room here in Valencia. Actually, for those of you that will go to the lab tour later on, you will see the equipment we have in the UPV fab where we do the wafer level testing. Our offices are in a separate building, which is this other building for, let's say, company entrepreneurship and hosting startups as well. And we are a small team still of 25 engineers, mostly focused on photonics, because that's actually what we do. We support other customers to develop their own products based on photonic integration, mostly focusing on the design and test, which are our core activities. And we were indeed a success story because we were the first spin-off company that was acquired out of UPV by the group of Hitachi High-Tech, part of the Hitachi group. So since 2020, the last 3 years, we have been part of this group. Let me maybe tell you a little bit more on that. Hitachi High-Tech is a large corporation in themselves. They are more than 12,000 employees, actually part of the even larger Hitachi group. Headquarters, as you can imagine, are in Tokyo, in Japan, but they have offices and divisions all over the world. And well, they have 3 main divisions. The first one, basically providing all kinds of instrumentation for medical sciences. I mean, for example, they provide tools for DNA sequencing. They do diagnostic and tools and spectroscopy and microscopes. The second division, nanotechnology, they provide mostly for semiconductor foundries etching equipment and defect inspection tools. Again, mostly for microelectronics, not that much for photonics because the market there is smaller. And then we belong to the last one, the Industrial Solutions Group, which is very much having the same business model as we do, in terms of they also provide services to other companies. And they provide all kinds of industrial solutions. In our case, we belong to the optical components department, which they provide all kinds of components from Japanese suppliers that they sell overseas through Hitachi High-Tech. So this is more of a trade company providing all these components. These are traditionally components that have been used for the assembly of optical transceivers for telecom and datacom applications, and that's still their main business. But now they are moving towards other areas where optics and photonic modules are built, like LiDAR, quantum, etc. So we actually came to complement all their activities with a technology that it wasn't under the umbrella, which is photonic integration technology with our own services. Having said that, our business model hasn't changed in the last 3 years, so we still provide all kinds of services in a pure play way. And we do that for many customers all over the world. A few of them in Spain, but most of our business is outside of Spain, unfortunately. We have worked with every other component, every other photonic company that you can imagine of that have photonic products in the market, mostly communications like telecom and datacom transceivers or microwave photonics, but also companies doing computing, both photonic computing and quantum computing or AI accelerators. Of course, in the quantum area, not only quantum computing, but quantum key distribution or quantum random number generations, as we have seen just now. And on the sensing area, companies developing LiDARs or biosensing devices like the OCT, optical coherence tomography systems, biomedical diagnostic tools, spectrometers, you name it. I think we have probably worked with any other application you can imagine. But independently of the application, we have seen that the trend on the last years is supported by many market studies. Here I'm showing the one of Yole, which is probably one of the most well-known ones, but if you check many other market reports, you will see similar conclusions, is that no matter the application, all of these sectors, all these growing domains are exploding. And by exploding, I mean that they have a compound annual growth rate of more than 30%. And this is, if you think about it, on a compound way, year over year, this is crazy. This is explosion of these markets, right? Clearly, the biggest growth lately has been seen in datacom transceivers, especially now with the emergence of AI applications. So clearly, this is a growing market. But there are many others that are coming. So it is the aggregated market for photonic integrated circuits that has been sustaining our industry in the last years. Independently of the application, at the end, the development cycle for a photonic integrated circuit is always the same. You start with an idea, our customers start with an idea, a system concept, and then we help them to materialize the specifications of such a system or the schematic or the diagram of this circuit into a specific technology platform. We have heard about silicon photonics, but we have also seen indium phosphide applications, silicon nitride, so choosing the right material platform still in photonics is key. And for that material platform, choosing the right foundry is also key. So we support customers in defining what is the optical architecture that is most suited to their application and basically defining the specifications together with them towards the techno-economical analysis. Once this is done, or if this is clear from the beginning, then we support them on the component circuit design and layout if needed. We help them on the manufacturing. We don't do any manufacturing ourselves, so we rely on third-party foundries that can tackle the manufacturing in a fabless way, either through multi-project wafers or dedicated wafer runs. Then one of our core capabilities and competences, which will be the characterization and testing of these chips or these wafers at VLC Photonics. And then finally, the outsourced packaging and test, which still is critical, as we have seen from the presentation from Peter from Tyndall earlier this day. So my talk today will be focusing mainly on what we see as one of the biggest challenges, which is still on the manufacturing, characterization, and packaging. Basically, first of all, considering the manufacturing, if you want to scale up your product, you have to consider that it will take quite a lot of time and quite a lot of funding. just an exercise, we did an evaluation of the amount of funding that was raised by many companies, some of them our customers, developing products based on photonic integrated circuits. And you can more or less estimate that the amount of funding over the years, and I'm talking about in average around 7 or 8 years to have a product in the market from scratch, can easily be more than 20 million euros. And I'm talking not only about the development of the photonic circuit, but the whole product itself, right? And that is not trivial. And in many cases, such an investment is required because some level of process customization is needed. These companies are known as fab-lite. So they are not totally fabless. They get involved in the manufacturing process, and because of that, they need quite a lot of investment to develop a part of the process. Of course, once you go into production, where the foundries will engage with you in a different way. You usually start by running some multi-project wafers, you get a few chips, then maybe you engage into some dedicated runs. But once you go into production, you actually strike a deal with the foundries to get a certain number of wafers per month under a certain yield conditions, okay? Independently of the runs. So you don't really mess about how many runs you do a year. But then you have to start considering other things, like for example, logistics. When you start to run tens, hundreds, or even thousands of wafers, logistics cost increases a lot. I'm talking about shipping, storing chips, tracking all these chips, insurances, you know, it gets into the different ballpark game. One of the things that you have to consider also is that when you are doing prototyping, every iteration you need to build your own masks, or the foundry will need to build those for you. But once you go into production, that cost is amortized because you reuse these masks. So that is good, right? But on the other side, you have to consider the fab yield, right? And that is what the fabs will work heavily when you move from prototyping and pilot production into higher volume production. Because at the end, the base cost will be based on the wafer cost, the processing cost of the foundry, let's say the operational cost of the foundry itself, and then of course, based on the yield. And ultimately, it will depend on the die size and the wafer size, and by doing this division, you will see what's the cost per chip. Let me give you some insights on this. In terms of the wafer yield, you have to consider what is the yield of the base wafer. In some cases, these are complex wafers with maybe 3-5 material epitaxis, which obviously are not 100% guaranteed. And then on the process yield, which is the yield that results from the lithography and etching steps at the front end of the fab. The die yield depends obviously on the wafer size. You have seen, for example, foundries like IMEC moving from 200 millimeters to 300 millimeters silicon photonics and greatly increasing the yield because of this. The layer stack, the more complex this layer stack is with more photonic waveguide layers or the more metallization layers, the more issues you may have with the yield. Especially in indium phosphide, the regrowth steps, and there are some platforms like the platform we have developed at GCS Foundry with TAVI platform that is epitaxy regrowth-free steps. Then, of course, the yield coming from the different front-end steps like lithography, etching, and deposition steps. The back-end processes that you may require for example, deposition of additional materials, or maybe, you know, grinding or polishing or coating, etc. And then some things that are related to the design itself, like the geometry of the circuit that you have or the volume that you will run on the wafers. So many people, when we start engaging with them, they try to do the calculation of what's the cost per chip at the end, or what's the cost per wafer, so I can do all my calculations of what's the cost or the price for my product. And you have to consider that that can only be seen once you have actually frozen the design. And that many people do not understand this, because foundries cannot start working on their yield if the design is not frozen. And that is hard to sometimes understand in the beginning. Let me give you an example. The die per wafers. How many dies you can get per wafer? The first example, we are considering a small indium phosphide chip, 1 by 3 millimeters chip, in a 4-inch wafers, like the indium phosphide wafer that Carlos just shown on the previous presentation. You can get almost 2,000 chips, okay? Bigger chip, bigger wafer, 10 by 10 millimeter chip, so this is, let's say, a large photonic circuit in a 8-inch standard silicon photonics wafer. you get already 250, more or less, around 250 chips per wafer. So you can see the order of magnitude here, right? If you move to a smaller chip in the same wafer, you get 4 times more chips, right? Let's say you take the same chip, 5 by 5 millimeters, in a 300 millimeter wafer, like 12 inches. So you get more than double. So you have to consider these numbers, because those are important also on the manufacturing scalability. So let's do the calculation. For example, how many wafers you will need, assuming 100% yield, to get 1 million chips, right, for your application. Let's say your transceiver or your quantum random number generation or whatever. First case, you will have 500 wafers. Secondly, you will need 4,000 wafers, 900 and 400. So here you can see some interesting trends, right? What do you think would be more interesting for a foundry from a manufacturing perspective? Clearly, the sweet spot is in here, right? In the 8 inches, on the second case, where you have larger chips, so complex photonic circuits, and let's say large size, but not crazy big, 12 inches, but 8 inches. Because then you are running many wafers, and that's what actually the foundries want, to increase the yields. You will be able to obtain the largest yields because of this. And you can see that maybe the case for moving to 12 inches in silicon photonics might not be that attractive if the chip is not that big and the volumes needed are not that large. Because obviously large semiconductor foundries, which are running tens of thousands of wafers per week, might not be that interested in a market that is only requiring 400 wafers for their application. So that also shows a little detail, which is that we are assuming here 100% yield, but in many cases this is not the case, because in many cases customers are developing their own processes or their own modules based on the standard process of the foundry. And in many cases it's still critical to have this characterization and testing to obtain the yields or to increase the yields. First of all, to validate the fabrication process itself, but also to confirm the intended layout functionality that the designers have intended, right? And be able to do non-good die sorting for packaging. When you move to production and you scale up, in many cases what we have seen is that customers still need fully functional testing on their chips, and it's not only PCM testing, so still a lot of characterization is required. And it needs to be done very fast and very efficiently to be able to do the non-good die sorting before packaging. And this means a lot of CapEx investment, because you need to parallelize these operations, right? So I'll show you what we have been doing to help our customers scale up through our services. First of all, we have seen that in the presentation by Peter O'Brien, how important it is to consider testing aspects or packaging aspects at the design stage. A proper layout is critical, considering test structures, design of experiments, built-in test circuits. This is critical. And also the placement of the electrical and optical connections is key if you want to have easy and fast testing and also packaging. Also, there is work with the software partners, EDA partners, to build these templates and this assembly or testing design kits for the different foundries on the layout software itself. So you can ensure that the designers can get this right before the chips are taped out, because later on it's too late, right? So we are working with these partners already to address this issue. Also, it's very key to have a proper test plan, because in many cases customers want to test absolutely everything, and I can tell you that indeed this will give you a lot of information, but it's not practical from a development point of view, because you need to be fast, you need to reach the market as soon as possible, and testing everything may be too cumbersome. So this is key to have this test plan, this agile methodology to work on. And it's also key to have proper operations in place. We have been working very hard over the years to have a quality system in place at VLC, to have everything, all the processes and work instructions documented, audited on a yearly basis, to have calibration of all the instruments, to have redundancy on all the parts. This seems trivial, but it's not at all. And especially with photonics startups that have limited resources, getting into this level of professionalism on the testing side is certainly an issue. And of course, ESD safe operations, because in many cases people don't realize how sensitive these photonic circuits are. And coming from photonics, maybe some of them are not used to RF, and this is really an issue. Of course, visual inspection is still a key from the package or the wafer to the chip level to detect all kinds of issues, from the epitaxy to the metallization to the waveguide definition, or even the handling of the chips and the wafers. This is very key, and it will avoid, obviously, many tests prior to the visual inspection. The probing, which is, as you know, one of the key things in photonics, because the tolerances required for photonic probing are very, very tight. Maybe not as tight as in the case of photonic sense, but in the order of probably half a micrometer alignment tolerances or below that. So we have different configurations to do that at the die level. We have developed over the years some characterization setups that actually we offer to our customers to do manual characterization of photonic chips of different configurations, both vertical coupling or edge coupling. And we are also partnering with Tsuruga Seiki as a partner, Japanese partner, to provide all kinds of components for these optomechanics setups for die level testing. We do have also some basic assembly capabilities, which help very much on testing complex circuits that would otherwise be difficult to probe, and in some cases this is very practical. You will see part of our characterization facilities in the lab tour if you plan to do that later today. We do have quite an extensive laboratory where we host a lot of instrumentation and probing stations to work from the visible wavelength to near infrared, 1310, 1550 nanometers, but also now working up to the mid infrared, 3 to 5 micrometers for sensing. We are also able to do electrical probing, DC and RF, up to 110 gigahertz, which is state of the art in modulation technology nowadays. And also, as I said, these basic assembly capabilities that I mentioned. On the wafer level testing to scale up, we do have a couple of fully automated wafer level testers from Ficontech, where we are able to do both edge coupling and vertical grating coupler at the wafer level, but also we are able to do that at the die level. So actually one of them is used for process development, while the other one is used for production. Well, we have pretty good repeatability on the measurements, very fast alignment, and this gives us also a capability to do fully automated data collection and processing, which helps also later on feeding the compact models for the designs of these components and circuits. As you can see here, we can also do die level testing on a fully automated way. Here you can see that dies can be tested directly from a gel pack. We have more advanced solutions where the chips are more complex to do that in some carriers. And eventually this can be scaled up through the partnership we have with Ficontech to be able to replicate that setup with not only the probing system, but also all the instrumentation and configuration of the scripting at our customers' facilities or at an OSAT of choice in Asia or whatever is needed. One of the key things, I believe, for wafer level testing to scale up, it's the edge coupling. Doing edge coupling at the wafer level, it's something that has been already, let's say, announced a few years ago, but still not so many people are able to do that reliably and fast enough. So we have been providing this capability already for 2-3 years, and basically it consists on embedding a periscope into a V-groove or trench on the wafer and being able to access the edge couplers at the wafer side. Honestly, this has proven to be very valuable because, as you know, coupling to vertical grating couplers still has some challenges in terms of losses or in terms of limited bandwidth, and a lot of people still want to do edge coupling testing because at the end, in many cases, these chips will be packaged with edge couplers. So they need to be able to test functionality with the edge couplers. Good thing is that you can play with the mold field diameter of these periscopes and be adapted to have different periscopes with different technologies. So that's, I think, the way to really go forward in scalability, to move from prototyping and to pilot production through wafer level testing. Some just takeaways for those of you that are actually planning to move into this direction and planning to have product development based on PICs. Still, many people claim that they are fabless, but fabless in the microelectronics industry doesn't really apply only to the manufacturing side, the front end, but also applies to the back end. And still the back end, as you have seen, is quite complex. the capex that you need to invest in clean room and probing stations and instrumentation and engineers is quite heavy. So if you want to do it in a scalable way, in a professional way, so it's hard to justify if you still don't have the volumes, clearly. And that's usually the case in many startups or spin-off companies. So my suggestion is to follow the successful model in microelectronics with working with a design test house and an OSAT to be able to scale up and let all of you focus on your core competences, which is on the system level IP and on the circuit level functionality rather than on the technicalities on the front end or the back end. So for those of you that don't want to follow my recommendation but still want to do your own testing, also we do some trainings on photonic characterization and testing, where we actually host some people here and in VLC Photonics in our laboratories, and we show them the basics on how to test some photonic chips. And we actually had one in April, but it's fully booked. So the next one we'll plan to do it in September. So if you are interested, please drop us a line, and we'll be happy to host you here. So that's all. Thanks a lot.
Thanks a lot. Are there any questions for Inigo? I do have a question regarding the going to bigger wafer size. You mentioned that the yield typically goes up quite substantially, but is that due to investing in new tools that probably have better processes, or is it actually the size of the wafer that makes the difference?
I think it's both, actually. So it is a contribution from the wafer size because of the wafer providers, right? And the yield there on the substrate will be probably higher. And then clearly there is a contribution from the processes that are more controlled, more homogeneous on the lithography and on the etching. So eventually the yield goes up by the combination of the two.
Okay, thanks. Any other questions?
Just curious, Inigo, on the yields you're seeing. So especially in the 3.5, you see much yield variation, or is there good yields? You probably can't comment directly, but just generally interested when you're probing at a wafer level, what kind of yields do you see?
Yeah, that's a good question. So yield probably is one of the best kept secrets for the foundries. But what I can tell you is that the yields that we are seeing in silicon photonics or silicon nitride are clearly improving over the last years, while in indium phosphide there is still more variability. But I have to say that working with this GCS foundry in the States and having developed this TABI platform, by removing the regrowth steps, the yield increase has been spectacular, because the regrowth is clearly one of the biggest contributors to yield. So if you are able to have all the epitaxial layers grown at once on the epi wafer, and then just let the foundry do lithography and etching, there is a great improvement on yield. So, but still, it's a challenge.
Thanks.
Yeah, during one course, I learned that in VCSELs, well, they told me that it was as low as 10% in the beginning, let's say in experimental stages.
It's not that low.
No, I assume it grows
yes.
when moving
but
to...
I think normally yields can start from, well, it depends of course on the maturity of the process and the level of innovation and research on the process development. But I would say it starts from 40 to 60 and scales up to 80, 90%. But again, this depends on so many factors that it's hard to comment here.
Hi, New. I just had a question. Usually the microelectronic industry is using test cards because that's how they get to the volume testing. And do you see how photonics can go that path?
Very interesting remark. Yes, indeed. Probe cards are being used in microelectronics, but the thing is that a probe card, first of all, is quite expensive to develop, several tens of thousands of euros or more, actually. So you only use them when you go into pilot production, and not so many companies move there. But On the other side, it's true that it's just electrical contacts, right? When you have to combine this with optical ports, let's say, it gets a bit more tricky. And there are some players developing hybrid electronic and optical probe cards, but at least on the optical probing side, they are still quite simple. So for configurations that have multiple probing ports on the optical side, it's still not the ultimate solution. But clearly for like simple configurations where you have like DC pads and maybe one optical port, this is already available, yes. And it's the only way to really scale up to millions or tens of millions of units, clearly, yes.
Another challenge to scale up a company in this field is to hire the right people. Yeah, I see that you are hiring. What would you say there is nowadays the situation in Spain, and what's your opinion about how to how to solve this barrier?
Yes, I think that's a worry for all of us. Most probably all the companies available here are hiring, right? And not only in photonics, also in microelectronics, and not only in Spain, in Europe, and not only in Europe, in the whole world. So I think it's a common problem for everyone. And Maite from BASIC earlier this morning mentioned that one of the key worries for the Valencia Silicon Cluster is actually to work a lot on the education and training of people at all different levels, from like institute level or high school level up to university and PhD, because actually we need this training, this workforce. And without that, no matter how much money you inject into the ecosystem to buy clean rooms and tools and equipment, if you don't have the engineers to work on this, it's going to be very hard to really grow in a sustained way. And I don't have a perfect solution for that.
Great, thank you, Inigo. Then let's thank the speaker again. Okay, and then we are at the last talk of today. Let's welcome Miguel del Canizo from Bullnet Capital. Miguel,
good afternoon. Thank you. Thank you. I'd like to extend a warm welcome to everybody gathered here today. But before I begin, I want to express my sincere gratitude to the organizers of this event for bringing us together and for their work in setting the stage for this great discussion, and of course showing uncommon persistence through the years. My name is Miguel del Cañizo, and as a founding partner at Bullnet Capital, I've been fortunate enough to engage with some of the most innovative ventures in the Spanish deep tech and especially in the photonics space, right from a very early stage in their life cycle. So our focus has been and continues to be on helping them to achieve their goals. So today I'm going to share insights in our 22-year-long journey in the development of support for photonic startups and spin-offs. Okay. So I will start my talk with an introduction to who we are at Bullnet Capital and what are our core convictions that underpin our commitment to investing in deep tech and more specifically in photonics. And from there, I'll delve in, I don't know if this is not very intense. The laser is not. From there, but anyway, I'll delve into our methodology, how we traditionally approach this investment work, and what our experience has taught over the years. Given that we are here at the Photonic Integration Week, it's a perfect moment to zoom in our special interest in photonics, a focus that has been a keystone of our activities from the very outset 22 years ago, as I was mentioned. Moving forward, I will be presenting our facts that essentially means showcasing our portfolio. a portfolio that is a source of pride for us at Bullnet. And I'm delighted to say that some of the companies are among you today. You will have, or may already have had, the opportunity to learn more about them on a stage, on the same stage, or to talk to the founders on the coffee breaks or in the B2B meetings. To conclude the presentation, and I will offer a forward-looking reflection on the strategic directions and resource allocation that we deem essential for the photonics community in harmony with Spain's industrial and educational systems. So, let me briefly introduce us. Bullnet Capital is an independent Spanish venture deep tech investment fund with 22 years of experience and around 180 million euros managed across 4 different funds. We are in Bullnet Capital 4 investing now. Our focus sharpens on the ICT B2B products triangle, including fields encompassing fields like electronics, semiconductors, software, medical devices, quantum technology, and notably photonics, all that now falling under the popular trendy term of deep tech. On this slide, and this is crucial, I want to highlight that while we don't drive the vehicle, the company ourselves, we are committed to making the journey smoother for those who actually drive for the team. With our extensive experience, that is a form of historical memory of the Spanish tech startup scene, quite all. We provide not only knowledge, but also common sense and external perspective to increase the decision-making and execution capabilities of the teams we support. Our primary goal of Bullnet as a venture capital firm is to generate substantial returns for our investors. But simultaneously, we approach our work with the convictions that it should also benefit society. This is achieved when our portfolio companies bring to market products that address social challenges, when we help elevate the value of our industry, or by attracting engineers, as Inigo was commenting, from top global tech centers to work here in Spanish startups. Thanks to successful exit involving our portfolio companies being acquired by world tech leaders as the ones that are mentioned there, our results in terms of returns for our investors are in the top quartile of the VC European industry. And well, concluding with the who are we section, our core team includes Jorge and Isaac, and I will not point with the laser to them, but they are there. And this team is complemented by tech advisors and friends from the research community. Most of them has been startup founders and successful entrepreneurs. And together with these advisors, they bring us both the scientific and the tech, I would say, international tech market experience, contacts, and opportunities to our portfolio companies, and give us invaluable insight during the selection process and during the company life cycle. Okay, so related to the profile of the companies we invest in, we target Spanish-based companies with a drive to be global, to go global. These firms are led by founders who boast impressive practical tech and scientific expertise, but merge with a keen eye for product development and customer engagement. Their approach is B2B. Their products are rooted in proprietary IP, serving niche markets that are either in their nascent stages or are rapidly transforming. What sets these companies apart is their unique technology. And how does it does that investment process work, actually? After, I will say that we enter in this stage normally, but there are exceptions. And after months of cultivating trust with the founding team and evaluating the project, getting deep into the details, trying to be sure that the technology is differential, that is really key. We initiate investment agreements negotiation with the team, and this typically means acquiring a minority stake and associated rights in the company for a multi-stage investment of several million euros, with the founders keeping the control. As I mentioned before, they are the drivers, and this it's responsibility. For our span of 3 to 12 years or more, we work, because that takes time, these sort of projects, we work closely with the team, leveraging our expertise in diverse areas, from recruitment and team growth, strategic roadmap guidance, IP policy, to negotiations with multinational OEMs, global scaling, sales support, securing additional funding, and even, and most of the time, managing partner conflicts. Our core investment belief, which have demonstrated in several occasions, is that in Spain it's indeed possible to invest in early-stage deep tech companies originating from research centers or in garage mode, and with investments in the range of a few million euros, we can help these firms in developing unique products for competitive markets, thereby attracting attention from major tech industry players. Such engagements typically yield substantial returns for our investors, as well as for the founders, the teams, and society at large. Why photonics? Our focus in photonics stems from Spain's Rhodes scientific and engineering teams with significant presence, entrepreneurial mindset, and product-oriented vision. You have seen several examples during the day. These teams blend complex technology, ranging from optics to quantum engineering to chemistry into products. And that, in some sort, aligns with our Spanish penchant for creativity. Spain has shown an incipient patterns of startups growing to merger and acquisition, so we have examples. And photonics, as an industry still in its growth phase, offers ample space for innovation, supported by, so far, at least so far, affordable infrastructure investments. And moreover, there is a growing interest from major players as photonic products, especially integrated products, begin entering the mainstream markets in devices and so on. This packet of slides from now presents our portfolio of 28 companies, showcasing our track record with successful exits, as well as some failures, from which we conducted through thorough postmortems, of course. A significant part, this is the track record, and the different exit and failures. A significant portion of the portfolio, as indicated, comprises photonic companies, and a focus was our third investments, Vision System on a chip, based in Sevilla, now belongs to Teledyne, Multiwave, Oncovision here in Valencia. KDPOF, Carlos will be here tomorrow. Wuptix in La Laguna, Twice Vision in medical devices from ophthalmology. Phyla, the founder is here. Sphere Photonics in the femtosecond metrology field. Bioherent, that Jonas presented this morning. LeapWave, Guillermo will present tomorrow. QSight, you just had Carlos. And deep detection, that's in X-ray cameras in Barcelona. And our two last investments, AFP Photonics. Some of the people of the team are here. And Pablo will present tomorrow. And Íñigo Molina, that's a founder also. And Mapsi Photonics, that we invested in last month. Well, additionally, a notable share of our investments are spin-off from research institutions and universities. As previously mentioned, beyond investment returns, we track various key performance indicators that includes the headcount growth with our portfolio companies, the number of patent submissions, the allocation of research funds, and the extent of co-investments leveraged, some of which we have are detailed here. Well, to conclude the talk, I'll share some insights on how to effectively channel our collective efforts and investment to cement the role we envisage for Spain in the global photonic market. That is a position not merely of aspiration, but one we are primed to occupy thanks to the talented individuals and dedicated professionals in this room. Public investment, like the one from CDTI, ICO, ENISA, and other institutions, is crucial, but falls short of neighboring countries' levels. And we have to not to forget that we are in a competitive arena, and we are far behind in some things. So money is important, but time is of the essence, and sometimes we are losing a lot of time. A spin-off legislation and university practice need critical enhancement. People are learning, but there are a lot of things to improve. In terms of human resources, we must navigate availability, cost, and the new dynamics of remote work that has a huge impact in our world, because competition from the big players is more easy for them now. University role is pivotal, setting the stage for our sector's future. We must maintain graded excellence, benchmark against top global institutions, and foster a synergy between academic and business-oriented research. There is also a need for innovative educational models, such as programs product and production engineers, for instance, and deep tech specialties or master degrees or things like that. Development infrastructures, particularly in photonics, are growing in complexity and cost. We all know that. So all that become crucial to stay competitive. But also we must take care and avoid chasing unsustainable trends and things that are trendy, but that are impossible. We face the challenge of increasing female representation in deep tech sectors, and we have a proof here with the audience. But well, we think that Spain public research can be a goldmine for creating spin-offs to change and revolutionize our production paradigm. Early customer engagement, finding the right investors, building dedicated teams, and shaping the social narrative are vital. So we think, as a conclusion, that we all must be proud of what has been done and be accomplished until now. That sets a great base for the future. but we must continue working towards it, and I truly believe it's worthy. So thank you very much and for your attention. You're welcome to talk to me on the cocktail or on the break. Thank you.
Great, thank you, Miguel. Are there any questions for Miguel? Yeah, I have a question regarding the fact that Bullnet Capital really engages in the company, in the startup, in this process. And does that also mean that Bullnet Capital is the only investor typically in a startup, or do you, let's say, collaborate with other investors and does this engagement?
Normally we are the first investor, professional investor, but we have co-invested with a lot of people, from Intel Capital to Trump, Incurside, a lot of Kaisa Capital Risk, people from international profile, technical profile, or financial profile. So, for instance, when international funds that are interested in Spain, they want to have a local expert on this arena, and that can be very near of the teams. So they are interested in co-investing with us, for instance.
Okay, thank you. Any other question?
So thank you, Miguel. Very good presentation. I wanted to ask you, how does it work? Do you usually do some scouting to find out all these companies, or do researchers or these companies approach to you? I guess maybe it's a mix of both. And from the moment you start having the discussions to the moment that you materialize the investment, I assume, of course, in every case will be different, but what is more or less a time frame?
Yeah, there is not a generic rule. There is projects that are in a phase more advanced, and the team is fairly complete. They have a business plan, that they have already a technology developed, I would say, even if it's a prototype. So this is very different of some cases where we have started working with the company even before the company has started to exist, okay? But normally the process, the investment process from the moment where we met for the first time to the investment could take 6 months, could be a yield number with the same error that the yield of the fund has. There is a lot of variations. We have been working with companies that started with even with no employee, no company, and we have worked with them during a year. But this is normally an exception because there are people that we know very well, or normally we prefer to, we don't have the bandwidth to do that with everybody, but sometimes we do that. Okay. The idea, for the process, we have to be sure that the technology is different, and here it's up to us to study, understand, talk to a lot of people, etc. And the second thing that is important is to create a trust relationship with the team, a mutual, because after the navigation will be long and hard, and you need trust from the beginning, and this takes some time. Okay. And after, the third part is negotiation, discussion, plan, how much money, valuations, all that stuff. Okay, but the three things are key, and that takes some months.
Okay, thank you. Any other questions? Okay, then let's...
It's late.
Yeah, let's thank the speaker again.
Thank you very much.
Yes, thank you everyone for this first day, which has not finished yet. So now we have for the next couple of hours 2 activities in parallel that you can subscribe. So one of them is organized by us, by my group. So it is a clean room and laboratory tour happening in 2 shifts at 5 and at 6 p.m. So half an hour lab, half an hour clean room, and then again at 5 at 6, 2 times. And the other one is what Sergio is going to explain in short. After both of them at 7 p.m. until 9 p.m., there's going to be some meal served also in the exhibit area. So of course you are welcome to stay with us. So Sergio, please.
Yeah, and for those of you who have meetings booked, you can see here for the first slot, it starts now at 5 o'clock. There are numbers on the wall. Then you just see if you are here, for example, and now at 5 o'clock we have in slot 1 Tony Perez with Peter O'Brien, and Rafael Gavazzoni and Pascual Muñoz, Raúl Anguita and Íñigo Artundo, and so on. And for those who are not here because you didn't book, you can just tell me please who you want to meet with, and I will try to connect you, okay? And I will be here in the room and in the corridor, and if you need me. You have 30 minutes for each meeting. You can sit wherever you want, but you see the numbers. 2 people here, 2 there, 2 there. You have the first 4 numbers here, and in that wall, the other 5, okay? Then those who go to the lab and those who start the B2B meetings, you can start. It's now 5 minutes to 5. I think we can start now.
Okay. Thank you, Sergio. Thank you all.